So just before we get on with a few other things, I just wanted to go through the key, most important things for the digital handouts. There's one formulas and definitions sheet that's provided mainly for the exercises, but can also be used actively if you have a printer at home or somewhere where you can have it easily available, or just up on your computer. Because there's a lot of these fundamental PVT equations and definitions that we'll talk a lot about in the days to come, and also use actively in the different exercises. So that's just I guess an FYI. It's just a few pages, and it's mainly just different sections of the face behavior monograph that we try to compile into here with the most important and relevant equations for this course. There's also some unit conversions, and so this nomenclature sheet for the for those of you who need that, with different symbols and what it means. So if you look at a slide and we haven't said it, I think hopefully most of it is given here. And also in terms of abbreviations, there's a lot of different abbreviations that we use. It's also at least an attempt to give some of that in this handout. And then we have two PVT reports. Again, just mention that these are synthetic, but they're more or less a copy of a commercial report for those of you who work with a lot of that. And again, the reason why they're synthetic is just because of confidentiality reasons, but it has all the information that is typically reported by the laboratories. And we have one example of a gas condensate PVT report, which is here. And we have and I guess also associated typical PVT test for a gas condensate reservoir. That's CC, CVD, and whatnot, these different experiments that we'll go through tomorrow. And then we have a same report for a black oil PVT study with the typical black oil PVT test. So we have compositions, we have CC, we have DLE, and also a multi-stage separator test. That's just so you've seen it, and hopefully you have access to it, and just send me an email if you haven't been able to access the material, and we'll make sure to also provide that. There's also a digital copy of the face behavior monograph that's in the course handouts. And please keep this within the family of people within the group, such that Curtis is not. What do you usually say there, Curtis?
Well, it's not supposed to be handed out. Do it as part of the course, and basically it's for your personal use only in connection with the course, and then we assume that you don't pass it to anybody but your family. If you got kids you want to start in the field of petroleum engineering, but yeah, it's basically for your own personal consumption, so to speak. So I don't want anybody having to visit me in a prison in Richmond, Texas, where the SQ got for anyway. That's appreciate you honoring that.
Yeah, that's just I think that's the general rule. At least if you do it, and Curtis has to go to Richmond, Texas, to jail, so you have to visit him. That's that's the general rule. Very good. And just to keep the red thread to the software as well. Everybody should have gotten login access there. Just use your go to courses.whitson.com. Log in with your email, the one that you have logged into this Teams meeting with, and then the password is just capital P, capital V, capital T, and then courses in small letters. 2020. And we're going to spend some more time on this later, but just to give you a brief introduction here, there's one oil field, or one petroleum field, a good petroleum field, that is uploaded here with that taps into both a gas condensate reservoir and an oil reservoir. We have one PVT sample from each of the wells. That's the PVT reports we have been provided in the handouts. And throughout the week, we'll look more at these. But for instance, the black oil table, the fluid properties at initial reservoir conditions, etc., is calculated and provided here, and we're going to talk more about that when we get to black oil tables and for instance gas EOR and other applications of an equational state that we'll look at later. I think what's important to emphasize is this equation of state that has been uploaded and is the one that's actually thermodynamically used in all the calculations that we'll do here together. And it's the one that's called SRK equation of state. We'll talk more about that later. And it has 31 components. And we use the so-called LBC viscosity model. So assuming that you haven't been exposed to this, you'll know much more about this later in the week. And we also have a gamma model that is one of the distribution models for C7 Plus that we'll talk about tomorrow. So assuming you haven't never seen an equation of state before, then this is a good place to just look at it, look at all the pieces that goes into the puzzle, and in the end of the week, you'll actually know what all these different pieces, important pieces mean, why they're there, etc. And the equation of state model that is typically a standard for the petroleum industry is a equation of state or a Ping-Robinson, has a EOS component property table and the binary interaction coefficients. And we'll all learn through the scope of the week what actually, here we have the molecular weights, we have the critical temperatures, critical pressures, we have critical, we have boiling points, we have omegas, we have eccentric factors, volume shifts, and we'll go through this systematically, what all these different columns actually means and why they're needed as a part of the calculations that we'll do here. Very good. So on that note, I think we'll just the next part. Is there any questions before we start this, or should we just keep going? If there's any of the material questions, just shoot me an email, and we'll make sure to get you all hooked up with all the material. Very good. So the next topic on the list is some phase behavior basics. My earlier, when we did we did this course multiple times also last year, is what I saw like in the end of the week. If we didn't pay enough attention and we didn't spend enough time on this introductory part, this is very easy to maybe fall off when it comes to more advanced topics later in the week. So I encourage everybody to pay attention here to make your life simpler as we move forward. But what we'll cover in this part of the course is, as we talked about earlier, we'll start with the petroleum fluids, and then the next topic after this will be fluid sampling. So we'll cover petroleum fluids, we'll look more into phase diagrams, we'll talk about reservoir fluid classification, which we kind of did a little bit simplified earlier today. PVT models, we'll talk about that. That's either an equation of state model or a black oil table in the petroleum industry. We'll do a much more deep dive into K values, and related to that, we'll also get into an exercise and some information about flash calculations. So here we'll have a lot of fun, I believe. But yeah, so very good. The first thing is petroleum fluids, and this is just a few components that might be typical to find in different hydrocarbon reservoir fluid systems. So here we have methane, ethane, propane that we know maybe from high school. We have isobutane, normal butane, isopentane, pentane, hexane, and also C19 here. I think a little bit simplified when we go into, for instance, on Friday when we're going to discuss gas EOR and more complex processes. At least I personally like to divide the hydrocarbons a little bit, or like all these components that is relevant for PVT purposes, into essentially some lean components. That will be, for instance, nitrogen, CO2, and methane. That's typical. They typically have a K value higher than 1. And then we have what's called the light intermediates, which would be, ethane up to butane. And then we'll have the middle intermediates, which is very hard. They're hard to define, but from when we talk about gas condensates or we talk about the gas injection, it's you can actually vaporize, so they can vaporize. And just for simplicity, we can just approximately define those from C5 maybe to C30, while the last group will be the so-called heavies, which is the components that cannot be vaporized in, for instance, a gas injection process. So that's maybe the components heavier than C30 plus, but strictly define the ones that can not be vaporized. And hopefully on Friday when we discuss gas injection processes and why, at least my brain like to simplify it like this a little bit into linear components, the intermediates, and the heavies, a little bit for the lingo, and also for understanding some key processes as we move forward. But it's safe to say that when it comes to petroleum reservoir fluids, they hundreds or thousands of hydrocarbons and a few non-organic compounds. The physical properties of these reservoir fluids depend on composition, temperature, and pressure. This we talked about many times already. That's essentially what PVT is about. Natural gas is composed of mainly low molecular weight alkanes, so that's the paraffins, which I'll touch more base on. It's in terms also CO2. Sometimes, if you're not very lucky, a lot of it can be H2S or nitrogen, which doesn't help from a burning point of view when it comes to burning natural gas. While most crude oils are composed of higher molecular weight hydrocarbon compounds, so that's paraffins, aromatics, and naphthanes. And that's the three main groups that at least we like to present throughout this course. Very good. So the first example of what we like to show, which is a very typical I guess compound or molecule or whatever we like to call it in reservoir fluids, is alkanes or more commonly maybe referred to as paraffins. It has the following formula structure, and this is a couple of examples of the paraffins, so normal butane and isobutane, and all the bonds. It's so-called single bonds between different carbons. The other example, which is what is I guess rigorously known as cycloalkanes, or which we think at least most commonly referred to as naphthanes, has the following structure formula, and it also has this circular shape. If you, I guess, draw it up like a when it comes to the structure. And the last example is or groupings is the aromatics, where benzene and toluene are good examples of that. And I think here the one key learning, or and also correct me if I'm wrong here, Curtis, but back in the days, and I think we still do that, is when Curtis and I guess other people as well got a new PVT report from a field in their hands, and they wanted to do something qualitatively. The first calculation that they did was to calculate the so-called Watson's characterization factor, which is can be estimated by this equation right here. It's also given in the monograph, the phase behavior monograph, equation 535, and it requires essentially two inputs. This is the molecular weight, and this is the specific gravity. And it's another thing that's important here is that you do this calculation on what actually has a lot of the heavier components in it. So that will be the stock tank oil, and you could either plot the molecular weight and specific gravity of the entire oil, or you can also back out the lighter components that are, for instance, lighter than C7 plus, and only plot the molecular weight of C7 plus or the specific gravity of C7 plus, and use that within the formula to get a particular number. But this characterization factor varies from around 8.5 to 13.5. And for these paraffinic compounds that we just looked at, it will be, if you have call it the paraffinic fluid system, you'll get a value between 12.5 to 13.5. And later today, we'll actually calculate this for our PVT reports. And if you're on the other side of the scale and you're more aromatic, then you're talking about a characterization factor between 8.5 to 11, and in between there, you have the naphthenic compounds, which is between 11 to 12.5. And it's important also to mention here that there's some overlap in the characterization factors when it comes to these three different families of hydrocarbons, and a combination of the paraffins and aromatics will obviously then appear to be somewhere in between, which here would be naphthenic. So that's just a note. But again, the first calculation that is typically done or can be done just to get a feeling for what we're dealing with is to calculate this characterization factor. And then we can plot, because there's two properties here, right? It's molecular weight and specific gravity that we can plot on this, for instance, a graph like this. If we have multiple samples from a particular field, we can plot multiple points on the curve here and see, or qualitatively and quantitative, see if the fluid system is either more paraffinic or more aromatic. And that's, I think, what we refer to as relative paraffinicity versus aromaticity, where increasing paraffinicity is then going down on this plot right here, which we'll use a lot later when we talk about the C7 plus characterization and getting a relationship between specific gravities and molecular weights. Good. So the non-hydrocarbons are typically found in different reservoir fluids. We mainly talk about nitrogen, hydrogen sulfide, and carbon dioxide. Many times they're found in reservoir fluids. CO2 and H2S are unwanted and costly to deal with. And nitrogen typically reduces the heating value, so it's negative. So not in general a lot of positive things related to these quote-unquote byproducts of production, but they're many times there. And from a thermodynamic standpoint, they depending on how much, of course, it is of the different components, can have a less or a more important impact on the PVT properties. Good. I think on this course, like when it comes to hydrogen sulfide, the largest amount, I guess, of in terms of a reservoir fluid, in terms of mole percent that you've seen.
Well, there are some really high ones in various countries. I think Kazakhstan and the Middle East. You have some reservoirs that really have high, more than 20 mole percent. H2S in the reservoir fluid, and it can even be higher. But yeah, that's in the North Sea. I think essentially 0 is, can be used for. There's probably exceptions, but that I don't know about. But I don't think I've ever worked with any field in UK or Norwegian fields that has significant. I mean, more than a small fraction of a percent H2S, maybe not even that. So, yeah.
Very good, and it's highly deadly. So we should be careful if you're on, like Hans Christian is out in the field today. So if any of you are going out to the field, make sure to know if there's H2S floating around in the air or not. So what we see on the screen here, just to do that first, is typical slate. This goes up to maybe C36 plus if you go to a commercial laboratory and get compositions, for instance, or measure compositions. So this is a typical slate where that you get from those laboratories. And the reservoir fluids contain thousands of hydrocarbon compounds and a few non-organic compounds that we talked about. The non-hydrocarbons are the CO2, H2S, and nitrogen. The pure components with known molecular weight is, from a hydrocarbon standpoint, typically from C1 to C6. Then we also have between maybe C7 to C10. Most commonly, we also have some isomers that are well defined, for instance, benzene and toluene. While at some point, either starting from C7 or from C10, we have single carbon number components. So that's C10, C11, C12. And for those of you who drill with the oil-based mud, to put that in perspective, the oil-based mud compounds are typically between C12 to C20 single carbon number. And just when we look at the grouping to the right here, we have the non-hydrocarbons being CO2, H2S, and nitrogen. We have the pure compounds, which is well defined, up to at least C5. And then from at least in many modern PVT reports, from C7 up to C, including C9, you have a mix of isomers and single carbon number components. And here we see that with, for instance, benzene and toluene and a few others. After that, they simply just group components into these single carbon number components, but they're actually averages of a lot of isomers that are between two boiling point fractions. So on that note, it's very important to emphasize that, at least in the cases where they measure all the isomers, that the single carbon number components are after the boiling points and not the number of carbon molecules. So we see an example of that right here. So here they measured actually a few isomers in the single carbon, or like some C7 component right here. And if we group it, this should be grouped into single carbon number C7. This should be grouped into single carbon number C8. This should be grouped to single carbon number C9, which might be not intuitive for some of you, that because you can actually have, for instance, this guy right here has 5 carbon atoms, I guess, and it's still grouped under single carbon number C7. So and that's based on the boiling point and not the number of carbon molecules. So that's just a heads up for that, if you need to kind of do this lumping yourself when you're working with a PVT laboratory report. And when it comes to these guys right here, they're actually components that are many more than 4 isomers grouped together, but they can be tens or hundreds of isomers actually grouped together, and we'll touch base on how many isomers you can estimate between different carbon number ranges a little bit later. But I think for C15, for instance, there's like 1,500 isomers or something that's just grouped into this average of C15. So so these are just averages, and this is when we characterize these components. We actually, for a particular field, try to find the average C12 or C11 component when we characterize that for our equation state. Compositional measurement. So when we measure compositions in the laboratory, the components that we talk about, we measure the mass of individual components with the GC. That's a good point earlier, that here we're mainly talking about oil, because for gas existing in a lot of the known hydrocarbons, we know the molecular weight, which we do not necessarily know for oil. When they actually, in most commercial labs, when they convert from the measured mass amounts to molecular weights, they use just some assumed molecular weights, typically cats per body. So this is from a commercial PVT laboratory. I think it's a Schlumberger report or something like that. They use either cats or Whitson, actually, which is I don't know if have they talked to you about these, Curtis? They're at least referencing your name on here, but you see the difference between the two here.
Yeah, if you look at the original cat spheres of body paper, they have points, and then they have kind of a line going through the points that starts to deviate at heavier molecular weights, and the values in the table didn't correspond to the line that they used to extrapolate. So I took those numbers off of the line that they had shown. And so what's given in the table versus what I basically read from their figure on this smooth surface. I can go try to fetch the paper and show it to y'all here in a few minutes. Yeah. But the difference is not big except for the heavier components.
Yeah. It's mainly these guys right here. From C22 and up. Yeah. So I guess what I'm trying to convey is that when we're talking about what they're measuring in the lab, they're measuring the weight fractions of each component, and that's converted to moles by using the total sample molecular weight and the individual components molecular weight MI. So, and they do that with this equation that we see right here, this guy. And the weight fractions is something they measure from the GC, and that can be, GC uncertainty to the weight fractions. And then the total molecular weight measurement has an uncertainty or an accuracy of plus minus 10%. So that has uncertainty to it. And then the in molecular weight of the individual components, it's depending on what component we're talking about, either known, which it is for these known hydrocarbons, and it's estimated for the single carbon numbers. While for the heaviest component, which in many of these labs is, at least now, it's typically C30 plus or C36 plus, for instance, it's highly unknown actually. So just looking at this table right here, here we have more of the quote unquote known ones, while everything here in terms of molecular weight. So then we're talking about the yellow or orange guy right there is estimated, and that's the job that we have to do when it comes to first of all capturing this relative permeability and aromaticity throughout the fluid system, and when we characterize the heavier ends, which is C7 plus characterization that we'll discuss tomorrow, I think. Curtis?
Yeah, no, I mean, basically the trick of taking laboratory measured mass fractions from the GC of the flashed oil to mole fractions of the flashed oil is involving these uncertain properties of the individual component molecular weights and the overall molecular weight of the flashed oil. So that's what this is saying. The numbers they give you in the lab report are not for mole fraction of flashed oil, or if separated oil has been calculated from flashed oil, then there's uncertainty there, and it's associated with the measured weight fractions, with the average molecular weight of the flashed oil, and with the molecular weight assumed for the individual component. So there's lots of small uncertainties, plus minus, getting you those mole fractions that we end up using in the equation of state calculations. So we'll come back in more detail to this later.
Very good. So I think the key takeaway here, we'll talk much more about the measurement of the compositions, the uncertainties, and whatnot, but we got a little taste of it in this section. But the key takeaway is that petroleum fluids contains hundreds of hydrocarbon compounds and a few non-hydrocarbon compounds that are unwanted and costly to deal with. Perfect. So before we move forward, any questions on this? You can also use the chat, I believe, if there's any questions there. So, well, then we'll just move ahead. So we looked at this once already quickly, and I think we'll probably look at it. Okay, we have one question.
Yeah, so for the SEN compounds, we talked about estimating the molecular weights, right? Can you just slightly throw some light on how those are estimated? Yeah,
so the molecular weights for the single carbon components, how they're estimated. Yeah, so the short story is for a particular, or I can actually maybe show that if we didn't have that right here. Yeah, so for a particular field, if we come to a particular field, actually one plot that we spend a lot of time on internally when we are doing studies, it's this specific gravity molecular weight relationship. So when we estimate not only the molecular weight that we just showed now, but also the specific gravity, the relationship between the two, that's actually derived from plotting the measured data points onto a curve like this, and developing a relationship between the two that's representative for that field. And that's what we call the relative periphericity or aromaticity. And when there's several different correlations for this, but we use one called the Søreide correlation most of the time. And he is actually Ingolf Søreide, actually works in Equinor now, I think, and he's an old PhD student of Curtis. But very quickly, that's how we would get a relationship for specific gravity and molecular weight for different, I guess, single carbon numbers. A little bit short, and we'll also talk about that more tomorrow. Anything to add there, Curtis?
I apologize. I didn't get exactly the question. I heard part of it, but didn't.
Yeah, so that was just the how we would actually estimate these single carbon number molecular weights for a particular basin.
Right. So you just have to use all the information that you have of measurements related to that molecular weight of single carbon numbers. Could be a true boiling point distillation data, where they distill off physically single carbon number fractions. They measure molecular weights, and you have an estimate from that. You have really indirect measurements that are like mini samples. If you have average molecular weights of the flashed oils and weight fraction of those flashed oils, then you can infer from the average molecular weights measured and the single carbon number mass fractions measured, you can find a correlation for MI that becomes consistent with those measured data. So they're not measuring directly the MI values, but they're measuring WI values that you assume are correct and average molecular weights of the flashed oils that you assume are correct. That would be another way to go about it. For C7, 8, and 9 components, you can actually, they provide today the isomers within each single carbon number. So you can actually compute the averages for C7, C8, and C9. So there's a lot of engineering you go into coming up with the correct values of molecular weight, MI. And we'll get into the details of that more tomorrow.
But a very, very good question, because there's a lot of things. And there's also a little bit depending, as Curtis mentioned, on what data we have available. So, if we actually have many samples from a field, that's very useful. If you have true boiling point distillation data, this is a special type of measurement, then that's very helpful, because it actually measures the molecular weights and specific gravity of each boiling point cut. So you can use that to develop this relationship that we just saw plotted. So we'll get a little bit back to that. But to find a relationship, we many times use we tune the Surrey correlation or another correlation to the available data, whatever data that would be, which is this specific gravity molecular weight plot. Good. Yeah, so we'll jump into reservoir fluid classification now. This is the second time we'll go through that, and I think it's even a third time where we'll touch base on it. But we're trying to look at it from different angles, just to make sure that this is really something that's in our backbones going forward. Rigorously, when it comes to classifying reservoir fluid systems, it's determined by two criteria. It's the location of the reservoir temperature with respect to the critical temperature and the Condon term. We'll talk about what that actually is, and the location. And that's a thing that might not be that intuitive for everybody. But again, it's back to the fact that PVT properties and PVT, at least black oil in the black oil sense, is dependent on surface process. There's also the location of first stage separated pressure and temperature with respect to the phase diagram of the reservoir fluid. So starting simply with the fluid system that many of us know from before, the black oil fluid system. So just to explain now we're looking again at the PT diagram. This is the initial reservoir pressure, and with time the reservoir depletes, so the pressure is reduced. These are the bubble points, and these are the dew points. While this is where we have the first stage separator conditions. So that's within the two-phase envelope. As we mentioned earlier, the oil is typically composed of more than 25 mole percent C7 plus, and the oil has a relatively low shrinkage when produced. And for those of you who like to think about formation volume factors or BOs, shrinkage is just the inverse of formation volume factor or BO. So shrinkage is just like the inverse of BO when produced. The equilibrium gas is relatively dry. So when you drop below the saturation pressure here, there's gas coming out of solution, and the components that come out of solution for a black oil are the lighter components. That's typically methane, maybe ethane, etc. But it's components that are dry and can be considered dry when produced at surface. So we can usually neglect the fact that there's also condensate in the gas that comes out of solution. That's at least a reasonable assumption. And in general, we have GORs less than 1,000 that we typically use as a rough estimate of what a black oil fluid system is. We talked about the two criterias for classification. So on there's 2 points here that we should take note of. This is the critical point where we have a critical temperature. And here on this axis, we have a critical pressure. And we talked about the two criteria being where actually the initial reservoir pressure and temperature is with respect to TC, and also this Condon term, which is I guess most to the left temperature that we can actually plot before it goes into single phase gas region to the right here. So that's the two things to take note of. A volatile oil, there are large shrinkages of oil with pressure is expected, and it's due to gas vaporization as the pressure drops below the bubble point. And the equilibrium gas that comes out of solution in a volatile oil case is relatively rich, and the amount of liquid produced from the reservoir gas is significant. So the dry gas oil black oil models cannot be used here. So here it's important that we actually have a way to capture the condensate that is in this gas that comes out of solution. And that's typically meaning that you have actually an equilibrium gas when you drop below in this region, that you have an equilibrium gas or a gas that comes out of solution that has components that is, you know, heavier than, you know, C6 plus in the gas that will translate into a condensate at surface. And the GOR range is typically between 1,000 to 3,000 scf per barrel. And again, here we actually see how at least the cartoon is changing the phase envelope as we move, and now we're talking about a gas condensate fluid system right here. Now we see that we've jumped to the right of the critical point, so we're actually in between the critical point and the pre-condensate term. So. And the components, the heavier components expand the phase envelope so that the reservoir pressure temperature lies between the critical point and the pre-condensate term, and the liquid drops out during depletion due to retrograde condensation. Further condensation also occur at the surface conditions. So here we actually produce, you know, above the saturation pressure, we're producing a single phase gas in the reservoir, but at surface where condensate drops out of solution. But as we go below the dew point right here, the saturation or the condensate saturation in the reservoir actually also increases. So that's a more advanced topic that we'll cover later. But the GOR range can be wild from 3,000, which will be, you know, near critical, to maybe even up to 150,000 scf per barrel. The wet gas is also a case we talked about earlier. Then we're at to the right of the pre-condensate term, and it's mainly composed of light hydrocarbon components. And the important thing to emphasize here is that during pressure depletion, we're not interfering with the two-phase envelope right here. So the wet gas will not drop out condensate at reservoir conditions, but condensate will drop out at the surface conditions. So the surface conditions is within the two-phase envelope. And the producing GOR typically is higher than 50,000 scf per barrel and remain constant throughout depletion. So you're producing a constant GOR, which means that you're producing a constant composition. So if you also took, for instance, this PT diagram and plotted it versus time, it will look constant if you plotted the produced compositions and the phase envelope of the produced composition. And the dry gas case would mainly be composed of very light components, such as methane and nitrogen and CO2. And it remains single phase in the reservoir, but also at surface. So everything is outside of the two-phase envelope. So in that sense, it's fairly easy to understand. But when we talk about dry gas, we should always think dry gas both in the reservoir and at surface. Single phase is the key word. And just here as a kind of like a cartoon, we're looking at the volatile oil reservoir fluid example. Here we start at the undersaturated conditions. That's what we call undersaturated conditions. We'll talk more about that. This is the saturation pressure, so which is a bubble point. And as we reduce pressure and we go into the two-phase region, gas bubbles form and rise, quote unquote. And if we, for instance, equilibrated a PVT cell at the pressure number 3 here, would actually have an equilibrium gas and an equilibrium oil. And as we talked about earlier, the first bubble coming out of solution of the gas bubble coming out of solution is what, and the composition of that is what we call the incipient phase. And vice versa, when we talk about a gas condensate reservoir at initial reservoir conditions, it's a single phase gas at reservoir conditions if it's undersaturated, and when we deplete it, the opposite happens, where actually oil droplets is forming and I guess falling due to gravity, and we're building up a condensate saturation. And if we did the same type of equilibration exercise there, we would actually get a gas and oil composition in equilibrium, where the oil saturation would be significant here at number 3. Very good. So now we're actually coming to a exercise, one of my favorite exercises, and it's an exercise which requires a little bit of explanation. The exercise, or what we're actually looking at here, you're supposed to fill in. Okay, we have a question. You can take the question first.
Yeah, sorry, in the previous slides,
Yep.
we talked about the starting condition of the various point, as which is as saturated, means undersaturated, and coming to saturation, right? So throughout the life of the reservoir, is it going to remain constant, or that is going to change, or how that is captured in these type of plots?
Yeah, so you're talking about the compositional changes of what's being produced?
No, the initial pressure, for example, it depends on the pressure, right? So the starting point, say it is undersaturated at the start of life, say after producing for 30 years.
Yeah.
So how does that change, and the character will change, the characteristic of the reservoir will change, or how does that affect the overall process?
Yeah. Curtis, you want to mention a few words?
Yeah, it was not completely clear, but let's say that we look at the change. What are the changes in the reservoir as you deplete? That's a good question. I think that's basically what you're asking. So when the reservoir pressure is from initial down to the original dew point, there's no changes in the fluid composition within the reservoir, practically. So that phase diagram you see there is the same. That will be applicable to the system as long as the reservoir pressure is at or above the dew point. Okay. Once you drop below the dew point, you will be removing the equilibrium gas phase for practical purposes, and what's left within the pores will become a richer mixture. So the pore composition will be changing, and it'll actually becoming richer. Richer meaning heavier, more C7 plus mole percentage in the pores. Now it's 2 phases, so it's split between an equilibrium phase of gas and equilibrium phase of liquid oil. But the total composition is changing in the pore. When that happens, this phase diagram that you see here will no longer be applicable. And what will happen is that the new one, when you reach a pressure P2, that new diagram it'll change the shape, but the most important thing to keep track of is that the critical point shown there will move to the right in the new curve. And as you deplete further and further, by the time you get down to, let's say, pressure 3, if you look at the composition in the pores, its critical pressure of what's in the pores, that critical temperature will then maybe equal the reservoir temperature. Okay? At some point, as you deplete through the reservoir, that critical point, the critical temperature of the new phase diagram will be moving to the right. And eventually that critical temperature will equal the reservoir temperature. And as you deplete further, what's in the pores would actually be called an oil composition, so to speak. So yeah, the phase diagram itself is changing, the critical temperature is changing as you go from dew point down. And there's there's a diagram in the monograph in chapter, I'm not sure which chapter, I think it's in chapter 3, that kind of shows that changing phase diagram as you deplete a gas condensate. The position of the critical temperature and the entire phase diagram is resketched. So that's, I don't know if that answers the question, but a lot of this phase diagram changes once you drop below the dew point.
Mm.
Yeah, and sorry, one additional question in association with that. It is actually, for example, does it mean that it is not enough if we take a sampling when we first drill a well? So do we need to take it as in the various life of the reservoir to correctly see replicate,
See what's
correctly
happening.
understand the and how the processing facility also will behave? What we are getting into the top sides or the processing facility. Is that right?
Yeah.
Means do we need to do it on a regular basis?
Well, I mean, you generally you'll keep track of the producing gas oil ratio, so you will see that. That change is probably the most important change. That can be tied back to the initial PVT study called the constant volume depletion that we'll talk about later. The constant volume depletion test gives you, in a sense, the expected producing compositions when you drop below the dew point. So you actually get that information from the original early sample CVD test. So you don't need to do new laboratory PVT tests of the well stream once you drop below the dew point. That's not usually done. It's not usually probably recommended. So does that answer the question?
Yeah. Okay. So what I understand is the initial test, what we do gives an indication of how it is going to behave later.
Exactly.
Oh.
The most important changes are captured by the CVD test. Yeah.
Oh. And is it applicable for an oil reservoir also?
The CVD test is not often used for an oil reservoir unless it's near critical oil. We use a different depletion test for oil reservoirs, but in principle, there's nothing wrong with using the CVD test. And if it's near critical oil, then we would even recommend it versus to use the CVD instead of the DLE, which we'll talk about later.
Okay.
Just 2 cents on this question, because we'll actually look at a video fairly soon where we'll look at how the produced compositions change through time. And we've actually plotted for a volatile oil and a gas condensate reservoir how the produced compositions and the phase envelope associated with that changes with time. But you have, and exactly as Curtis says, two things almost changing at the same time: what you produce at surface and call it the phase envelopes and compositions associated with that. But then you also have something that remains in the reservoirs, in the pore space there, that will be a different composition that you will have its own kind of different phase envelopes through time. So it's very important to acknowledge that these compositional changes, when you're not producing something that's undersaturated or single phase, is a dynamic process, and the compositions change through time, and sometimes a lot.
Okay.
Thomas?
Yeah, one question more about the sampling nature. If you take a sample with high drawdown and exceed the dew point, is there any chance to fix this later on?
Yeah, that's an excellent question, and we have a section on that later. So what we recommend to do for those cases called equilibrium contact mixing to essentially correct for this exact issue that you talked about, and we'll cover that later today actually in the fluid sampling section. So that's definitely possible.
Okay, thanks.
Gerardo?
Yeah, just regarding this topic, I'm not sure when to ask the question. We've seen quite often that when we go into condensate fields, there's an underlying oil rim and somehow the oil rim, when you look at the properties of it, it really does not have any relationship to the actual gas condensate that is above. And I'm talking about, you know, the GOR that you would expect if it was in equilibrium with the gas condensate, or the bubble point actually is not really, it's really off. So are those conditions more related to some other process that is not capturing PVT?
Yeah, so if you have a gas condensate reservoir with an underlying oil rim, and in this case you actually have you know, samples from both the oil rim and the gas condensate region as well.
Yeah.
Yeah.
And you're
So,
saying what is not the same?
Well, if you would think that if the oil rim is a process of lowering the pressure on this gas condensate, and then it drops out, and then you create the oil rim, then you will imagine that, for example, right at the pressure where the oil and gas condensate are situated, it has to be coincidental with the dew point of the system.
Right, so the dew point of the gas sample would equal the bubble point of the oil sample would equal to the pressure at the GOC.
Yes, that's correct. And then
what you find is what?
Yeah, and when you find that it's not the case, and you can't blame it on sampling conditions, and there are several fields in Halton Terrace, for example.
Yeah.
Yeah.
So this paper and the discussion, what Matthias was mentioning, this equilibrium contact mixing method, laboratory and calculational method that will be discussed, should handle that, treat that situation in great detail. There are many different scenarios why you have the gas not having dew point equal to the oil bubble point, not equaling the initial reservoir pressure of the GOC. There's a number of different reasons for them not being equal, but this discussion in the sampling will try to deal specifically with that case. So why don't we go ahead and we'll come back to that when we reach that. Yeah.
Thank you.
Yeah.
Very good. Very good. Okay, very good questions. And a lot of it is very relevant to actually what we're going to talk about later. So now we have two questions somewhat related to ECM. And that's great that we're going to cover that later. So good stuff. So we're going to jump into an exercise now. And then we'll probably do a yeah, we'll see a little bit. Okay, so the exercise here requires a little bit of explanation. Again, here you can you need to try your best because I can't stand as I usually do in the in-house courses behind your shoulder and see if you do it right. But now you can just do it probably in your living room or wherever everybody is right now. And what we're going to try to do is from the top of our minds how we understand PVT and reservoir recovery processes at the moment, sketch out how we think the stock tank oil recovery factor, so the recovery factor that a lot of people are talking about, is changing as a function of solution GOR. And when we talk about solution GOR here, what we're actually talking about is fluid type. So, you know, as we talked about when it comes to fluid classification, we covered the entire gamma of fluid types from low GOR black oils, which will be, you know, typically here, and then we'll go more and more into, you know, volatile oils, near critical fluids, which will probably be closer to here. Maybe we have something like this, near critical fluids. And the more we go to let's just assume that the critical point is somewhere here, critical point, and the more we go to the right, the leaner the system is, and we go into the gas condensate region and potentially dry gas all the way to the right. So what we would like everybody to just do right now is to just sketch out how you think the oil recovery, the stock tank oil recovery factor, is changing as a function of fluid type. So just think about this as fluid type as we move from left to right or right to left. So spend 2 minutes on that, and I'll take the time. Just sketch it out.
So just one assumption, I think you might have mentioned it, but just assume that the initial reservoir pressure is the same for all systems. You mentioned that?
Yeah, that's
and
good.
Yeah, and that it is undersaturated to some degree. Okay. Yeah. Somewhat undersaturated. So you have a single phase constant composition reservoir that's initially undersaturated somewhat, and you abandon the depletion of that reservoir is brought down to 100 bar, whatever, from, let's say, initial pressure is 600 bar, the abandonment pressure is 100 bar, and the saturation pressure, just as a hint, will vary as a function of this initial solution GOR. So the distance from the initial pressure of 600 bar down to the dew, that'll change as you put different stuff inside the reservoir. So you need to think a little bit through that. We've already talked a little bit about it, but those are some behind the scene assumptions on trying to, so we're just saying Mother Nature gave you a fixed pressure and temperature, but that it charged with different mixtures, and it's a uniform fluid system. So what, how would the recovery factor look like depending on what, Mother Nature charged into the reservoir? A low GOR oil, a high GOR gas, near critical fluid. The only thing that's different is what is being charged into this reservoir that otherwise is identical. Temperature, initial pressure, abandonment pressure, everything else is identical.
Very good. So then just go ahead, sketch it out, how we think it looks like. And remember the assumptions from Kurz. That was a very important note, actually. Same initial reservoir pressure, same abandonment pressure, somewhat undersaturated. And we can also go through how the saturation pressure changes with GOR. But this is just to stimulate, I guess, the thought process of or try to communicate actually the fact that PVT is really, really important when we talk about reservoir engineering in general. And as you'll see, there's a lot of things going into the final results, as we'll also go through, and we'll probably save that to a nice Q&A session later this week. So I'll give everybody 90 seconds more. I'll time it now, and we'll get back to it. Okay. Has someone can just raise their hand? Has someone seen this particular plot before in any paper, any presentation? No, that's It's actually a very nice plot, and that's maybe also another thing to communicate. You can actually find out that there's a small. I made a source very small to the left, so people couldn't cheat. So you can actually find the answer in that paper from 2005 or 6. But I think we'll just jump into the answer real quick, unless would someone like to try to explain what they think is the answer, or we'll just go to show it. Yeah.
And maybe you could just ask, if you're way out to the right, this crazy, essentially dry gas or wet gas. I mean, let's say it's a wet gas. Way out there, it's a wet gas. It's single phase gas in the reservoir throughout depletion from 600 bar to 100 bar. So there's no condensation in the reservoir. So you don't have very much stock tank oil, right? You've got 5 barrels per million standard cubic feet being produced, but you're getting 5 barrels per million from day 1 to the end of abandonment, right? So what can somebody suggest what the recovery should be there?
Very low.
Okay. Any other thoughts? Do you think it would be a low recovery because there's a low amount of stock tank oil in the system?
Well, I think that the recovery is supposed to be high because, as you said, we won't go below the dew point as such. So
yeah,
we will take all the liquid up to the surface in the gas phase, and then it will drop out. Then.
Yeah. So basically, you're not going to get very much oil recovered. That's true. So the N won't be very large. But in fact, for the wet gas, if you get at the end of abandonment from 600 bar to 100 bar, let's say 80% recovery, just to pick a number, it'll be close to 80%, maybe 90%, but let's say 80% recovery of gas. Okay, if the gas recovery factor is 80%. In fact, the oil, this light, condensate being produced in the wet gas will also be 80%. So it'll be the same value, same recovery factor in the condensate as in the gas. So it'll be high, let's say 80%. So you can just put that point there somewhere in your figure. It'll be high. The amount of N is small. The amount of oil that you're going to recover is not very big. But the efficiency is very, very high, as high as you can get. It's 5 barrels per million being produced day 1, 5 barrels per million being produced at the end. So that's kind of the one extreme. The other extreme to think about is, what if you have this dead oil, 10 cubic meters per cubic meter? Okay, it's highly undersaturated oil. In fact, there's no bubble, practically no bubble point. So you've got 600 bar initial pressure, assume no water drive, no water influx, no compressibility, or there's compressibility, but no water drive. So the only recovery you get is because of the expansion of the connate water, the compaction of the pores in the rock, and the expansion of the oil itself from 600 bar to 100 bar. So what kind of recovery does somebody want to suggest what they think that recovery would be of stock tank oil for that very, very low G oil?
Yeah, less than a digit recovery. We're talking about 3, 4, 5%. 3, 4,
5%. So I think that's exactly what you'd see. Depends on the compressibility of the rock and the water and so forth, but 3 to 5%. So at the far left, you've got almost, well, it's not nothing, but it's something, but it's very small. And to the far right, it's essentially as high as it can get. It's 80, 90%. So at least we have those 2 points. Does anybody not follow why you get those 2 points? We can come back to that maybe at the end of the week. But I think those are 2 important points. Now, what happens in between is complicated. I think is not intuitive.
Mhm.
But maybe those 2 points you should try to work through yourself, at least during the week, and we should revisit it on Friday maybe. I think, Matthias.
Yeah.
Those 2 points are very important that you understand. That's really basic expansion. It's kind of like it's fairly fundamental. So I'll let you go through the answer, Matthias, with him now.
Good. This is how it looks like. The final answer. Yeah, and the as Curtis said, very high on the right, very low on the left. We actually do not have any simulated points, but just let's say or something like this. And in between, it's complicated, and we see that we actually have a local maxima here and a local minima right here. This is the critical point. Just for simplicity, for now, we'll have a special session on this later in the week. But for now, I think we can just say that the recovery to the right of the critical point, so when we're talking about gas condensates, is PVT dominated, while in between is in this region when we're talking about two-phase also production, it's PVT and rel perm related. So I think we'll have probably a special session on this maybe on Friday, Curtis. So I guess what we wanted to convey here was just you know, a lot of these things are complex. This is not intuitive, but hopefully by the end of the week we are able to understand and pinpoint a little bit more of the reasoning of why this is happening right here. But to understand that, we need to understand what saturation pressures are, how we expect that saturation pressures change as a function of GOR, for instance. That's a fundamental thing for this understanding, where we have bubble points typically increasing to some maximum, maybe close to the critical point, and then on the dew point side, it's also decreasing, but it's a non-monotonic function. Okay, very good. Did someone guess it correctly? Gerardo, did you have it?
No, nothing. I'm just delighted to see the answer. Yeah.
Okay, now we can say that to everybody. PVT is super important. That's good. Yeah, and this is just thoughts for ourselves. Why is it like this? As we talked about, it's PVT, very important PVT, but it's also some rel perm effects there that we'll get back to. But if you understand the PVT, then it will be much easier for you to also understand why it is like that and why it's has that complex shape. Curtis?
Yeah, and I think the fact that when you have rel perm effects, it's the hybrid or the combined effect of PVT and the rel perm, how they interact with each other. So high shrinkage oil, you know, that oil saturation drops very rapidly. That has a big effect on the KRG and the KRO. Recovery goes down. So there's a lot of interaction between PVT and rel perm in that left region where it's got the maximum.
Very good. And now we have a video, the video that we talked about, which was related to one of the questions earlier. I can't exactly remember who asked it, but I think an important distinction to mention here that I tried to convey earlier is that we're going to look at a volatile oil case and a gas condensate case. It is simulated data for an unconventional well in the US, but the same things apply. As soon as you drop two-phase, and what you produce at surface actually changes. But as Curtis also mentioned, there is, you know, the composition of what remains in the reservoir will change, so that will have its own PT diagrams, and what you produce at surface will have its PT diagrams. And what we're going to look at in these videos is what we see at surface in terms of PT diagrams. And that's just to communicate that this is a dynamic process. So I think we'll start with the this guy right here. So I hope everybody sees the screen. So just a little bit of explanation here. We have the bottom hole pressure plotted together with the saturation pressure. So the saturation pressure here is in green, and when it flips potentially to another fluid type, it will change color. We also have the GOR plotted here in purple. And the producing GOR is around 1,500 scuffs per barrel, so volatile fluid. And we also see here the phase envelope of the in situ fluid. So if we look at this when we start, so this is the pressure in black here, and when we start the depletion, we see that as long as this pressure is above the PTM or the phase envelope, what we produce at surface is constant, while what we'll see when we drop below is what we produce at surface. So remember that this is what is produced at surface will change. And it's a dynamic process. And this is just for one example, but it's to communicate that these things is changing, and at least for complex. And what you actually see here is that the saturation pressure of the produced well streams actually changed from a bubble point to a dew point over time. And this is a very, very rapid decrease in bottom hole pressures, which is the signature of unconventional wells. And then the same goes here. This is for a near critical gas condensate well. The way we know that is that we have a temperature that's to the right of the critical point, and it's again just producing GOR, the saturation pressures, and the bubble points. And if we run this video over time, we see how the produced fluid compositions or the PTM envelope changes as a function of time. Or what's produced at the surface. So this is a dynamic process, and what's a little bit unique with these unconventionals is that the produced fluid compositions, because of this rapid decline in bottom hole pressures, change extremely fast, maybe much faster than what is expected in conventional reservoirs. So it's interesting from a fluid perspective in that sense. Any questions? Anything to add there, Curtis, or anybody else?
Yeah, no, maybe worth watching one more time. Just it's a lot of information there.
Yeah. Do the GC case one more time. Again, above the saturation pressure, the PT diagram is constant. So above the dew point, doesn't change. And as soon as we drop below the saturation pressure, in this case, the PT diagram shrinks.
And the point here is that this is the phase diagram of the sample that would be collected for the producing.
Yeah.
And
so,
yeah, I referred earlier in this morning that to how the phase diagram would change within the pore itself. That phase diagram would look very, very different than this.
Yeah.
So, comment on that.
So this would essentially be the case where I think we got a question about that when it comes to sampling. So if you went to the field every single day, sampled separated gas and separated oil, recombined them at the producing GOR, and measured the saturation pressure and created a full phase envelope every single day, and plotted that versus time, this is kind of what that is in just a simulated manner. Mainly just to communicate this dynamic process. Thomas, you had a question?
Well, this what we see on the surface is Is this including the Relperm effect as well?
Yeah, so this is what we see on surface. So this is a gas condensate reservoir. What's a little bit characteristic of these gas condensate reservoirs in unconventionals is that the producing GOR and the bottomal flowing pressure are kissing, I think, as Curtis calls it, very closely here, the black curve or the dew points, sorry, which means that actually the condensate drops out of solution until at least this point remains immobile, and everything that you produce is essentially the gas and whatever oil you have in solution with the gas, or condensate in solution with the gas. And that's Relperm related because the mobility of the oil that drops out is then zero.
So basically the mobilization of condensate is in the moment when the GOR goes down again, or when it goes down for the first time, actually.
Yeah, exactly.
Yeah.
Very good. There's one more question.
So we noticed that the PT diagram, the envelope started shrinking, and then at one particular point of time, say at near this 3000 psi, can see we at the critical point or something that stops, right? So at what point does that stop, and then it gets into this two-phase region?
I think probably that departure is where you get boundary dominated. You start seeing the effects of boundaries, kind of a conventional depletion. Whereas prior to that, it's more infinite acting. You haven't really felt the boundaries yet of the well box boundaries. So that's basically what it is. The saturation pressure is essentially equal to the flowing bottomal pressure in unconventionals during the infinite acting period. And then once you start reaching boundary effects, then they will depart, as you see here. So that would be, I think that would be the right answer, if I understood the question right.
Yeah, and that's also So it's probably not that relevant for those of you who not work on unconventional resources, but I think probably most of the companies, at least here, has some unconventional assets. So it's relevant for that. But it's a little bit specific for these these horizontal multi-fractured wells and unconventionals. But the main, I guess, key thing that we wanted to communicate is to understand that once we're getting into two-phase into the party, then things are changing dynamically, both down in the reservoir and what we produce at surface, and sometimes it can be drastic changes through actually short periods of time as well.
Yeah.
So I think we'll just continue for 25 minutes. I'll promise more breaks after lunch, but we'll do 25 more minutes, and then it's a break from 11:30 Norway time at least until 12:30, and then we'll continue. Does that sound okay? Okay, very good. So now we're going to discuss phase diagrams, and many times we've seen a lot of these phase envelopes and PT diagrams for multi-component systems, but we're actually going to take a step back now and talk about phase diagrams of pure components. And for those of you who remember that from university, if you plotted pressure versus temperature for a single component, you would get something like this cartoon in front of us right here, where at the top right we have the so-called critical temperature and pressure, and right here we have just plotted in atmospheric pressure and the associated boiling point. So if this was water, this T right here would be 100 C. The line that connects these 2 points is the so-called vapor pressure curve or vapor pressure line. At this point, you might wonder, why are we actually learning about this? But trust me, when we talk about and we get to equations of state, we're going to use this actually directly to explain some of the more complex things there, centric factors and other things. So we remember to pay attention here. What's I think important to emphasize is that above this line right here, we're talking about this component being a single phase liquid, and below this curve right here, we're talking about a single phase gas. Anything else to add here, Chris, or is it good?
That's good.
As we have talked about many times in this course, we're talking about PVT. So now we're actually going to look at this is the PT diagram for a single component at a particular temperature, and we take a slice through that to plot how it looks like versus volume. And I'll just play that back. We start at this pressure right here. We reduce the pressure until we reach the vapor pressure, and at the vapor pressure, still at constant temperature, there's actually something happening. We're getting a gas phase, and at this vapor pressure, it goes from essentially being 0 vapor to close to 100% vapor. And as we cross this line, it is 100% vapor, and we can continue to plate at that constant temperature. And I think we can do this exact exercise at the different temperatures, and we actually get a PV curve as we see to the right here, where what's in the blue region is the so-called two-phase region, and I bet a lot of you have seen this type of plot from different courses in chemistry or in university yourself from before, for single pure component phase behavior. Okay, so good. So now we're going to remember that, as we've at least gone through that once, and we will remember that when we talk about equations of state. But most, I guess, quote unquote important or commonly talked about in petroleum industries, at least, these multi-component, which we have talked about already, but just to define this a little bit more rigorously, such that we get this into our backbones. When we look at a PT diagram for a multi-component system, we have a set of bubble points in green, indicating oil or liquid. We have a set of dew points in red. We have a critical point where essentially the properties of liquid and vapor converge and is not possible to distinguish. And then we have the critical temp, or the Crecon term. It's this tangent right here. And we have the Crecon bar at the top right here. That's just a little bit of nomenclature. And many times when we see these plots, there's also some what's called equal volume lines or quality lines. There's some different names for that, where I guess the saturation along this line of liquid, for instance, would be the same versus vapor. And yeah, and above the green line, we have single phase oil, and both to the right and also below this lower dew point line right here, we have single phase vapor, while everything in between here is two phases. And that's what we're going to talk about now in the next section before we take a break. Okay. So just what we're going to look at now, we're going to look at something we've looked at we looked first at fluid classification from a GOR C7 plus perspective. Then we looked at just the PT diagram. And now we're going to include an additional dimension of complexity where we're actually going to plot the liquid relative volume curve versus as a function of pressure for the different fluid types. And the way it's just defined as the liquid volume divided by the total volume at some pressure and temperature, where the VO refers to the oil phase. So going from the initial reservoir pressure to the bubble point in this case, as we see right here, the liquid relative volume is 1. It's constant because everything is liquid, and 1 over 1 is 1. And that's so advanced I go into math here. And then below this point, we get the so-called, we call this a shrinkage curve, where gas is coming out of solution, and the liquid relative volume drops or shrinks, which has the opposite shape of or the shrinkage curve is also associated to this. So this is for a black oil reservoir that you also have in the slide deck right here. When I guess most times when if there's like a debate whether or not it's a black oil or a volatile oil, not that actually matters that much, but I think rigorously what we like to use, at least internally, is that if the liquid relative oil curve is linear, we say it's a black oil, while if it has a bend to it, a curve, we say it's a volatile oil, which we'll look at here. So again, the same things apply. One thing that's typical is that a saturation pressure for a volatile oil is typically higher than a black oil. Also, that's why we have the bubble point more to the right in this case. And we see that the relative oil volume curve has a bend to it, and that's kind of the signature of a volatile oil. And the more steep this shrinkage curve here is, the more near critical it is. So if you have something would be all the way to the critical point right here, you might have something that goes almost vertically down like this. Now we're talking about the retrograde condensation. So we're between the TC and the pre-condensate term for this example. And we know that above the dew point, we have no liquids. This number is 0 because we have a single phase gas. So here we're plotting points that are 0. And what happens when you drop below the saturation pressure is that the liquids is dropping out of solution, and it actually is non-monotonic. So it reaches a maximum before it changes curve. And this is the part that's condensation driven or dominant, while here it's vaporization driven. And this is related to be able to explain this, we need some more vocabulary and knowledge in our toolkit. So we'll go through this later when we get to understand and talk more about K values, which is what we need to really understand this non-monotonicity right here. Very good. And for a wet gas case, we know that the VRO is always 0 in the reservoir. So the liquid relative oil curve is simple. It's always constant and equal to 0. The only thing is that at surface, we're producing inside the two-phase envelope. And the same goes for dry gas. The only thing is that, again, we're on the outside of the two-phase envelope. Very good. So If we, for instance, just for the sake of, I guess, example, take a vapor-like component, can be methane, and we can take a oil-like component, for instance, decane, and we mix those in different proportions. So what we see here is the vapor pressure curve of the single component. If it's 100% either methane or decane or something like it, and we mix it in different proportions. So if we say that the vapor mole fraction, so if we have, 10% of it is the vapor of the total mixture, we can get a fluid that looks like, or a PT diagram that looks like this. And here we're talking about a black oil. So this is back to what Curtis talked about with phase envelopes and how it changes. Black oil with a GOR between 100 to 1,000 scuds per barrel. And here we probably should have said stock tank barrels. So just remember that. If we increase the FG to 0.4, for instance, the critical point is shifted to the left, and we get a different phase envelope. If we continue to do this, maybe in a 50-50 split, we actually have something very near critical. What it means with being near critical is that the reservoir temperature is close to the critical point and temperature. When we flip all the way to the gas condensate region, we also see how the critical points are going more and more to the left. Now we're actually having the temperature on the right side of the critical point, and in the end we actually have a temperature that's all the way on the outside of the PT diagram. Now we're talking about a wet gas, which is 50 to 500,000 scuds per barrel, and this is just a dry gas case that we try to plot onto there. Very good. So now I don't think we'll talk more about reservoir fluid classification throughout this week. We've done it 3 times now, so hopefully everybody should have it super solid in their backbones at this point, I hope. And we'll test that immediately with grades in the next exercise. And this is a table, I think it's table 2 in the monograph that was handed out, where you see some examples of compositions up to C7 plus and some associated properties. We talked about APIs, for instance, right here. That was a question earlier for different fluids. You can see GORs and you can see OGRs. You can see the specific gravity of gas. You can see saturation pressure, Watson characterization factor that we talked about earlier, molecular weight and specific gravity of CF7 plus. And then we see the compositions of these different fluids right here. And now I would like everybody to take 2 minutes. I'll time it. We'll do 2 minutes, and then we'll ask what's actually wrong with this table. So there's a typo in this table, and for those that you're now like one up against the monograph, which is always good. It's a flying start to career in PVT. But learn, like now we've done reservoir fluid classification 3 times from 3 different angles, and we see that we have dry gas, wet gas, gas condensates, near critical oil, volatile oil, and black oil. And there's something wrong with this table, and I'd like everybody to, on the note, write down what they think is wrong with it, and then we'll open the floor for suggestions in a few seconds. So 1 more minute, and then we'll get back to it. Yeah, so we got a suggestion here. Yeah, so we got good. So I actually would like everybody. That's a good. I like that. If everybody can write in the chat what they think, that would be great. Because then we can get some different opinions. And it's not necessarily intuitive, or there's so many things here, right, that can confuse people. But somebody that there's. Yes, we got one suggestion that was a good suggestion, and that's actually a suggestion we get very often, which is it because of the dry gas being less than the C1 of a wet gas? And that's a good observation. And the thing we have to remember is that when it comes to the reservoir fluid classification, there's two criteria that is important. It is where the reservoir temperature is with respect to the critical temperature and the pre-condensate term, and also where the surface process is with respect to the phase envelope. And only the compositions of C1 doesn't violate those two constraints. So that it is actually something else. So the problem with what's wrong with this table, and if you have a copy of the phase monograph, and I think it's table 2, just cross out this number right here, and that's just a typo. And because here it suggests that we have a wet gas with a saturation pressure, but as we just talked about here, this is a wet gas, and a wet gas is defined such that there should not be a saturation pressure within at reservoir conditions. We should be to the right of the pre-condensate term. So just take a note of that, and that's a very good, I guess, observation.
Now, this would be entirely correct since I wrote the book, and there's plenty of mistakes in the book. But if the saturation pressure that's reported there was reported at the reservoir temperature, in other words, if that saturation pressure is at reservoir temperature, which I'm not sure what it is for this wet gas, then it would be obviously an error, because then it's not a wet gas. But that saturation pressure could, I suppose, be at some lower temperature or something, who knows? But yeah, I stand corrected, no problem. But the point is the saturation pressure always needs to be related to a specific temperature. So
that's good. So it can either be that this either it's a different temperature, or it's just a typo, or it can also be a mislabeling of the wet gas potential. Like if it had a saturation pressure, then it would actually be per definition a gas condensate. So multiple things, but at least good if you thought in these lanes, I guess.
You could try to recreate it, right?
You can, but yeah. Very good. Yeah. So this is the answer. There's one exercise, exercise 1, that's handed out in the handouts. We'll actually skip this exercise because of some other priorities, but it's also provided there. So if you want to do it, you can do it, and the answers will also be provided in the end of the week. So it's not mandatory, but just if you like to do it, you can do it. So that's under exercise 1 in the provided handouts.
You can just show the Excel file because it's just a plot.
Yeah, it's actually just a plot, like Bilal said here. We'll just jump out of this.
Just open the solved version.
Yeah. The solved one.
Yeah.
That's the nice thing about being the teacher. You have the sold versions. Second. This one? Yeah. So it's just a simple plot, and not something we wanted to prioritize in terms of time because there's so many other things we want to go through this week. But it's trying to just do the exercise that we just went through with some for some different fluid types. And here we use butane and or pentane and methane. Yeah, so we'll provide that in the handouts as we go through the week. So we'll get going with the next topics now. There will be a little bit more, like we try at least to have more exercises after break, just to make yeah, it's easier maybe to do exercises than when people are getting a little bit tired of listening to me and these things. So we'll have some exercises that will be done and gone through, especially one in Excel, and then will be one more here on the go in the PowerPoint as we go forward, and obviously just Q&A as needed. So we have enough content to cover here. So we'll just get started with the next topic, which is PVT models. So that's what are the different options we have, at least in the petroleum industry, to model fluids, and in general, these models are used to establish a PVT relationship for different fluids produced from a basin, a field, or a and all the engineering calculations require two fundamental properties for a given pressure, temperature, and composition. And that's the amount of each phase, the density of the phase, and the viscosity of each phase. And when it comes to the PVT models that we'll talk about here, and which is also used in the oil and gas space, we're talking about black oil PVT tables and the black oil PVT model, and the compositional equation of state model. And both of those we'll learn about this week. And most common, a compositional or an equation of state model is typically the most quote unquote sophisticated. And at least modern black oil tables are 9 out of 10 times actually derived from an equation of state model. So they're very, very much related. We'll start with the thing that came first, with the black oil PVT model. We discussed that a little bit earlier, but I think to emphasize is that black oil PVT tables and the black oil PVT model is used in a wide range of reservoir engineering disciplines. You have reservoir simulation, well testing analysis, pipe flow, process, just to mention a few. And I would probably say even for reservoir simulation, it's much more common for at least depletion performance and general reservoir simulation modeling to use a black oil table rather than an equation of state in a so-called compositional reservoir simulation. That doesn't mean that we should not have an equation of state, because as I mentioned, these black oil tables are most often derived actually from equations of state, and it's just that format we're inputting into the simulators. When it comes to, from a high level, what actually creates a black oil table, which is a key piece of the black oil PVT model, which is one of the key PVT models, is so this is what we call the two-component model, right? And the oil being the one, surface oil and surface gas being the two. And in a generic black oil table, we have we typically have pressures, and then for the oil we have three different parameters. The so-called, this is the solution GOR, and then we have the BO, which is the oil formation volume factor. Then we have the viscosity of the oil. That's the viscosity. And similarly, on the gas side, we have the viscosity of the gas. We have the formation volume factor of the gas that we'll talk about, the dry formation volume factor of gas, and that's important, gas formation volume factor. Then we have the solution solution CGR, many times also called vaporized oil ratio. So in some simulators, most people are used to this. The little RS is the SBE nomenclature for that property. Okay, so that's how a generic or a general black oil table looks like, a table with pressures and we'll get a little bit to it. It's a little bit more involved than just this, because we have an undersaturated and a saturated part of the table. But for all practical purposes, when you look at it, it would look something like this. Again, it's a two-component model, and the model parameters is the ones that I just mentioned right here. And the way we represent the composition, which is one of the key things of PVT. PVT was pressure, temperature, and composition. So the way we, or the surrogate for composition in this model is the ratio of gas to oil or oil to gas. And the model, which is very important, is dependent on the surface processing. And when we talk about surface processing, it's either a very, very complex surface process, or it is a simple separator train with the number of stages and the temperature and pressure of each of those stages. And this is just, again, to emphasize one thing we mentioned earlier, is that black oil tables can be used for all reservoir fluid types and not only for black oil system. So the second time we repeat it, and probably the last, but it's an important thing because many people confuse the black oil fluid system and black oil tables, that they are related. Well, actually, a black oil table can be used in a much broader sense than only for black oils. Good. So we talked about that it's process dependent. PVT properties are process dependent. So here we are looking at this is at reservoir conditions. The stuff right here. The green is supposed to be a cartoon of a liquid phase at reservoir conditions, while the red here is supposed to be a gas phase at reservoir conditions with an associated dew point, and vice versa for the oil with an associated bubble point. And if we bring this to the surface and we process it to surface products, we use a special nomenclature for that, and it's actually to make our lives easier. And this is a part of the presentation that is important to I guess pay attention to, because it hopefully will make our life simpler as we move on forward in the course. So these different symbols, so these volumes right here are all surface volumes, and the first subscript, the one with the hat on, is indicating what is this volume at surface. Is it a surface gas or is it a surface oil? While the second subscript, which does not have a hat, is referring to the oil phase that it's originating from. And since we can have both a oil that turns into stock tank, or a reservoir oil that turns into stock tank oil, and a reservoir gas that turns into stock tank condensate, if you like, it's important to have a way to distinguish the two. So just to go through this a little bit systematically, the first one at the top here is a surface gas originating from a reservoir gas. The second here is a surface oil originating from a reservoir gas. That's typically what we call condensate. This guy right here is a surface gas originating from the reservoir oil, and this guy right here is a surface oil originating from the reservoir oil. And just by introducing that nomenclature, we can actually start to define the different PVT properties, where the dry formation volume factor for gas, we'll define that later, is defined as the surface or the reservoir volume of gas divided by the surface volume of gas originating from reservoir gas volume. The little RS, this is what we also call the large RV in a lot of simulators, is the surface volume of condensate divided by the originating from the reservoir gas divided by the surface gas originating from the reservoir gas volume. Similarly, on the oil side, we have the formation volume factor, which is the reservoir volume of oil divided by the surface volume of oil originating from reservoir oil. And the solution GOR is the surface volume of gas originating from reservoir oil divided by the surface volume of oil originating from reservoir oil. And pay also attention to the coloring here. So these properties are process dependent, while we also have the viscosities right here, which is process independent. So they actually don't, they're not affected by the processing at the surface. And in a quote unquote traditional black oil table, a black oil table that assumes that we don't have any condensate in solution with the gas, the assumption is that the VO hat G is 0. So this guy right here is assumed to be 0, which is in general a wrong assumption and only valid for dry gases and maybe low GOR oils. So then again, this important message related to the processing is that 1 meter cube is not always equal to 1 meter cube, because changing the surface process, we actually might be able to get more meter cubes out of the same reservoir barrels. So remember that these things are process dependent. And now we're going to walk through each of the different properties, unless there's any questions, and see how they change with pressure. Good. So we start with the black oil properties. So again, defining the BO and the RS. And if we plot these versus pressure, so now we're at some single phase pressure, and we reduce the pressure until the saturation pressure. So this is what we call the bubble point. And above the bubble point, the composition is constant, and since we use solution GOR as a surrogate for composition, the solution GOR should be constant. What we see when it comes to the oil formation volume factor is that above the saturation pressure, it actually, with decreasing pressure, is actually increasing, and it actually reaches a maximum at the saturation pressure. When we reduce the volume further below the saturation pressure, gas is coming out of solution, and the solution GOR goes down. That's the solution GOR of that reservoir oil phase, because it's releasing, quote unquote, the gas, such that there's less gas in solution in what's left. So the solution GOR goes down, and it follows the exact same trend as the BO. And actually, if you plot, which I think we'll see later, BO versus RS, it will be a straight line here if it's if we're talking about saturated properties. Any questions? Okay, good. The viscosity is has a little bit the opposite shape of the oil formation volume factor. So above the saturation pressure, it actually decreases until it reaches a minimum at the bubble point right there. And then as more and more gas is released from the oil, the viscosity is increasing. In the single phase region, there's also, for those of you who know, for instance, the isothermal compressibility equation, that can be calculated from the derivative of dB over dP, and the BO itself with this formula right here. And if you like to calculate the reservoir oil densities, you use the following equation right here. And for those of you who have seen this before, or a long time ago, or never seen it, it might look like this is some kind of a correlation, but it's actually not. It's derived from material balance. Yeah, so this is not a correlation, but it's just honoring the material balance of the surface products that has been produced from a reservoir oil phase. So it's with perfectly closing.
Numbers and conversion factors.
Yeah, numbers is conversion factors for field units. Curtis?
Yeah, the standard cubic feet per barrel, stock tank barrel, and pounds per cubic feet.
Yeah.
The only comment I have on the compressibility term is that it is it's what we call a directional quantity, because this applies, it's only correct, the isothermal compressibility, when it's written this way, if the pressure change is in the positive direction away from the bubble point. In other words, you're staying single phase. There's no change of amount in the oil phase. If you're at the bubble point and you calculate this compressibility starting at the bubble point, and you drop the pressure 1/10 of a psi instead of going to a higher 1/10 of a psi, you get completely different compressibility numbers. So that compressibility term there is for, but I usually write a plus on it because it means that the pressure change has to be in the positive direction. We can come back to that later. If somebody's doing well testing, it makes a big difference in calculating compressibilities that are used in well testing when you go below the bubble point. So anyway, I can get back to that later.
We good? Yeah, and this was what we talked about. Or it was actually not what we talked about, but typically when we represent or input, for instance, a black hole table into a reservoir simulator, for instance, you're actually not only inputting one composition, so one solution GOR, if you like, but you actually input a table of different saturated properties with different associated undesaturated properties. So just to make that clear, for instance, for this fluid right here, which has a RS equal to RSB4, this part right here will be the undesaturated region, while this part right here will be the saturated region. And that also is the case for this guy right here. And if you, as I said, I think that's what we're going to show right here. If you plot the saturated BO versus RS as a function of each other, now for two different fluid systems. So this one is, as we had learned earlier, a black oil system. Shrinkage curve is, or shrinkage is more or less linear, or the BO is more or less linear below the saturation pressure. The same goes for vice versa for the volatile oil, which has a more curvature to it. But no matter if it's a curvature or not, if you actually plot it as a function of each other, they exhibit a straight line type of behavior, as you see here, plotted for two different APIs, a volatile oil and a black oil, 30 API versus the 45 API. And this is just the correlation that's used to visualize that the concept as well. But we'll see that when we generate black hole tables from the equational state, I think on Friday, that you'll see the exact same behavior on the oil side as what's given here from the correlation. Yeah, you want to mention a few things about this, Curtis, or?
Yeah, just the limitations of 1,000, maximum 1,000 standard cubic feet per barrel.
Yeah.
Maybe not even that much. Glossa correlation, which came in around 1980, developed by Øystein Glossa here from Trondheim, extended based on measurements he made on North Sea oils to higher GORs, maybe as much as 1,500 standard cubic feet per stock tank barrel. So that's a little better for the more volatile oil systems. And yeah, I think that's it, unless there's any questions.
I can add one more comment here on this plot. So when you plot this BO versus RS, what you see that when the RS goes to 0, BO doesn't reach to value of 1. So that's indicated here with the blue text. So because like RS is equal to 0 means that there is no solution gas. Okay, but with no solution gas, still you can be at some higher temperature, where the oil the oil volume at reservoir condition doesn't reach the oil volume at surface condition. And when you take that oil from the reservoir condition to the surface condition, going from higher temperature to lower temperature, you get some thermal expansion. So that's what that's why this BO is not equal to 1 when RS is going to 0 from this correlation.
And I think physically the thermal expansion should be somewhat dependent on density, which it's not.
Yeah, in this correlation.
So yeah, so it loses accuracy at low pressures, and if it's treating only the thermal expansion part, it's not that accurate.
Good. So now we've covered the key concepts on the oil side, and now we're going to look at something a little bit more complex, probably, which is on the gas side, gas-related properties. Again, here we get the definitions up of RS, which I now for the third time also call RV, and the BGD. We'll talk about why it's important that we include this D later, right here. But we have noted a saturation pressure on the plot, which is the dew point. And then as we reduce the pressure, we know that the composition, the surrogate for composition when we talk about a gas, it's the solution CGR, and that should be constant above the saturation pressure that we've learned. And the BGD, which is the formation volume factor of gas, is the inverse is called like an expansion factor. It's when the pressure is decreasing, this property is increasing. And when we drop below the saturation pressure, condensate is coming out of solution. And the BGD continues to increase, and the RS is dropping down until it actually reaches a minimum right here. We've seen this actually earlier as well. And at very low pressures, it actually becomes what's called non-monotonic, which just means that it reaches a minimum and changes direction, I guess. And the reasons for this will be discussed later. So hang on tight for that exciting session. I mentioned briefly here the importance of, or why we emphasize the usage of D and not just call this BG. And that's because there is actually a difference between the so-called dry formation volume factor for gas and the wet formation volume factor for gas. The dry formation volume factor for gas, the one that we recommend and is the correct one in general, is the one that assumes that that in the reservoir there might be condensate in solution with the reservoir gas phase, so that actually there is an RS that is higher than 1. In a lot of the conventional textbooks, I think especially in reservoir engineering, if I'm not mistaken, Curtis, the definition for B or gas formation volume factor is actually typically the wet gas formation volume factor, as we see the equation for right here, which assumes that there is no condensate at surface. So in cases where there actually is condensate in solution with the gas, you're actually just converting this to a fictitious surface gas volume that is not correct. So Curtis, a few cents on this?
Yeah, no, that's right. The nomenclature was difficult to choose and decide on when we did the monograph, but effectively the traditional gas formation volume factor assumes everything that's reservoir gas becomes surface gas at the surface. That's the conventional. So there is no condensate from a wet gas, there's no condensate from a gas condensate, which is of course bizarre. But the reason we call it wet gas is because when you convert a reservoir gas volume to a surface gas volume with this BGW, you get an artificially high surface gas volume. We're calling it here wet gas. In Canada, they call it fat gas. and it's literally because it's fatter or bigger than it should be. You're not going to sell that volume of gas. In fact, you're going to sell less than that volume of gas. And what you don't sell as gas, it's going to be condensate or oil. So you just have to kind of basically, when we call wet gas, we don't use it too much in this course, but when it's used, this wet gas or fat gas or whatever you want to call it, it's basically assuming that everything that's reservoir gas becomes surface gas at the surface. Reality is what's above. Reality is that with the exception of a true dry gas reservoir, which is why the nomenclature is a bit strange, if it's a true dry gas, quote unquote, reservoir fluid, then there is no surface condensate, right? So why do we call this on the top dry gas? It's because the gas being sold has been dried of its condensate of the liquids. It's been dried by a multi-stage surface process. It's been, so that it's not a good name, but that's what it is. So basically it's a sellable gas. It's the surface separator gas volumes. And then it's, yeah, so I don't feel like I'm explaining it very well, but you just have to kind of learn the difference. The key is that for a gas condensate reservoir, the difference in the two numbers can be from 1% different, which is not big. That would be for a real wet gas or lean gas condensate, to 15 to 20% in error. So if you're using the wet gas VG in your black oil model, your Eclipse 100 model, you may be anywhere from 1 to 20% off in all of your gas in place volumes, oil in place volumes. Everything would be wrong by that amount. So it's something you can't ignore. You have to kind of just read chapter 6 and chapter 7, chapter 7 and chapter 6 in detail until you understand it. If you don't understand it now, based on this not very good explanation. It is important. So it's your obligation to understand what is the difference.
And just see, we have a question. I think we had a question, but we can go back to that just before we go there. For those of you who would like to see the derivation of these formulas, just please send me an email, and we have some videos that goes through that if that's of interest. Curtis also mentioned the impact of this, which was very good in terms of difference in condensate production. The nice thing about this is if you use the wet gas, you're kind of underpredicting the amount of condensate. So actually doing it correct will be also better and will be nicer to communicate to management and whatnot in the companies, because it means that you have more reserves. You'll make more money selling the condensate than the gas. So it's a lot of positives using the dry formation volume factor. This one recommended, and not the wet one. That's important.
And if you double dip, they'll fire you. So that if you put in BGW into your Eclipse 100 model and you put in the RV, then you'll have 20% too much gas in place, and you'll have 20% too much oil in place, and that basically the result is you'll be looking for a job. So if you're consistent, then it's better than being inconsistent. So.
Yeah, Matthias, on that line, yeah, I just wanted to comment that you know, in JOX, which is the software that calculates volumetrics, right, for exploration, yeah, it's not very clear in practice, and I'm very glad you touched on this, because it's the problem with JOX, it's how they account for this is you either go dry gas and then you assume a correction factor for processing, or you either go the biphase formation volume factor. But I've seen many projects where they go both ways. So
yeah. So
really
you only lose your job if they catch you.
yes, that's the downside.
Yeah, but no, it's something that really requires diligence on the part of all the engineers using these, which, you know, management, economics, everything. So it's, but like I say, there is quite a long discussion of it in Chapter 7 in particular, and it's worth going there if you're just confused right now.
The Gerardo, what was the name of the software? Was it GeoX?
Yes, GeoX, which, as far as I'm aware, many companies in Norway use it. I don't know outside of Norway.
Okay. Is it that who developed that software?
It was, you know, like many softwares, it ended up being bought by Schlumberger, but I think it was developed in here. And again, over there, it gets a bit confusing, because most people assume that the surface correction factor relates to discounting CO2 volumes, for example, from the gas volume, or it relates to the efficiency of the processing on how much liquid can you actually extract. But most of it actually relates from the difference in between assuming dry gas and biphase expansion volume factor.
Okay. Very nice. Good. Yeah. So just yeah, for people who where this is clear, great. If it's not clear, also just send me an email. We have some more I guess content and whatnot on this to get you up to speed. But it's a very important difference. But just to make your life simple, just imagine that there's you know, only use the dry gas formation volume factor in general, no matter what fluid systems you're dealing with. Because if you're dealing with a dry gas reservoir or a black oil where it's really not important, this RS term right here will go to 0. And if you solve this equation when this is 0 and you compare it to this equation right here, you'll see that they're actually the exact same ones. You see that very easily from here if this thing goes to 1. So to make your life simple, always use this no matter what fluid system, and you'll hopefully be safe if you do it consistently. Yeah, and this is just an example of a concept. Yeah.
So what that means is that even if you notice there's a bit of you expect that you have wet gas or some solution gas in your system, you should still use PVTG, for example, in Eclipse, not PVTG.
Yeah, how should I explain? I mean, how should I put this? If you're using gas volumes that are true sales gas volumes, okay, that are physically being metered and sold, then you need to have the BGD in whatever engineering calculations you're making. And you need to know the stock tank barrels of condensator oil that are with that are in a sense being processed out of the well stream. So but if you're just looking at the BGD or BGW, which one to use, it has to do with whatever your engineering calculations are. If you're using true sellable gas volume, then it should be BGD. And that's 99% of the cases. So, and that's what's the only thing generated from an equation of state, PVT package, PVT SEM, PVTP, phase, whatever it is, will be the BGD if you ask for Blackwell tables. So you're safe. But if you start using other programs that start calculating the BGs from DAKE or in the reservoir engineering textbooks, they will be calculating BGW. And again, it can be wrong by quite a bit. So what dictates which one to use is simply if your engineering calculation uses true sellable gas volumes that are being metered, and then you need to use BGD. That's okay. The only case I can tell you that where the BGW should be used and would normally be used is in gas material balance. So 99% of the programs doing gas material balance engineering that use BG, but then the cumulative gas volume that they're working with shouldn't be the sellable gas volume. It should be sellable gas volume plus whatever condensate's produced with it converted to gas equivalent. So it's called a wet gas volume. So that's the material balance is about the only time one should be using the BGW.
Good. And I think a general rule of thumb is that every time you see a BG and you don't see as other subscript, you should try to find out whether it's the BGD or the BGW that is actually presented or calculated. And from there, go in and find out, is this consistent or not?
Yeah, exactly.
But Curtis, since you made this comment that before material balance, you can use BGW, then I guess people who use MBEL, then in MBEL, like when you use this gas condensate option, there you can enter the full Blackwell PVT table. Like you can have BO, capital RS, little RS, and BGD. So there, if you then you just have to study what methods MBEL used. For example, doing material balance calculation, is it using when it is using GP, the cumulative gas produced, is it using the dry sellable gas volumes in the cumulative gas production, or is it using the wet gas volume?
Yeah, that's right. So no matter what the program you're using, if the program is asking for sellable true gas volumes being metered, then you need to use the BGD. And if it's asking for or using surface gas volumes that are not those, that are these so-called fat gas or wet gas volumes, then you need to use the BGW. So that's right. Yeah.
And if you're using BGW to calculate for doing material balance calculation, then the in-place volumes you get are the wet gas in-place volumes, and the surface condensate is not it's not a straightforward calculation for surface condensate that you just multiply it with little RS and you get the surface condensate.
That's right.
Very good. Very good. So I think we've conveyed this now. At least that it does matter. It's very, very, very important to know the difference. And we should use the BGD when we're talking about sellable gas volumes. This was trying to indicate here from this slide as this is only valid when we're talking about or dealing with dry gases, because then there's no condensate at surface from that reservoir gas phase. This is an interesting topic with a lot of answers, and deals with how we actually calculate all these properties that we just went through. Back in the I guess heydays, we used correlations. They're still used some in some cases, typically for low GOR oils, or if you're dealing with dry gases as well. They could be calculated from PVT data, so you can actually take, for instance, a DLE, which is an exercise tomorrow, I think, where we're going to try to at least use a DLE experiment and correct it for separator conditions. But that's also valid only when the GORs are less than 1,500 scuffs per barrel. The general recommendation and what's used as an industry standard is to first create an equation of state and then use that equation of state to generate the black oil tables, which will be discussed more on day 4 and 5. And how to develop an equation of state will be discussed more tomorrow and Thursday and Wednesday. Good. And that this is just a reference of the differences between modeling with a black oil simulator versus an EOS reservoir simulator, written by Eivind Fevang Singh, which is one of our colleagues, and Curtis. And I think Eivind is now chief reservoir engineer or chief engineer in Equinor, for those of you who are there. There's also an exercise 2 here that we will skip, but at this point we're going to do exercise number 3, which is quite involved. It will take a little bit of time, and Bilal will actually share his screen when we get to that point to walk through the solution step by step. But the overall goals and objectives is to, first of all, understand fundamentals moles to mass conversion. So we'll use some equations for that. We'll apply both the ideal and real gas law. So that's PV equal to nRT and PV equal to Z nRT. Be able to convert compositional data to different averages, whether that's molecular weight, specific gravities, densities, and volumes, and then use the so-called standing C factor chart, which is a part of old school, quote-unquote, engineering. And what we actually will do is to calculate the solution gas-oil ratio with approximations of the surface process. We'll compare this to the laboratory PVT report. And we'll calculate the gas C factors and compare it with the lab data, and also calculate the dry gas formation volume factor. So a lot of things that we talked about now that we'll put into practice into an exercise. So first thing to do is to find the exercise itself, which is within the exercise folder. So it's exercise number 3, and it should only be one Excel sheet that we all can open. Here we will also need some equations from the formula sheet, so have the formula sheet available as well. And then on that note, so this is how it should look like, the sheet that you'll have. On that note, I'll probably just hand it over to you, Bilal. But we'll use these formulas on the formula definition sheet right here, and then we'll use this Excel sheet and try to calculate the values. So, do you want to share there, Bilal?
Okay. Yeah, before we jump to the third exercise, I guess Matthias said that we are skipping the second exercise, so I can just show you why we are skipping it, because it's already something we have gone through, and it's just using the standing correlation. And okay, maybe I just open the solved version, so you see what's there. Okay. Yeah. So in this in the second exercise, or what we were planning to do is to use this standing correlation that's equation 3.111 in the ST monograph, and calculate this BOB, which is the oil formation volume factor at the bubble point at different values of the solution gas oil ratio at the bubble point. So these are just the input values, and then calculating this value of A in the standing correlation. And we have two cases, so both are at the same reservoir temperature. We have the same surface gas gravity, and the surface oil. The only difference is the surface oil density. In this one, it's 0.9, and here, in this case, it's 0.8. And we are doing the same calculation for both cases and just plotting this BOB versus RS. So bubble point formation volume factor versus the bubble point solution GOR. And you see it's the same plot that we showed in the PowerPoint with two different slopes. So the slope of the BO versus RS depends on the surface oil density. And then again, you see that at 0 RS, the oil formation volume factor is higher than 1, which is indicating that there will be some thermal expansion. And what Curtis mentioned in his comment, that the correlation gives you the same value at RS equals to 0 for both oils, but this thermal correction or this thermal expansion of the oil, it should be dependent somewhat on the surface oil density or the density of the oil, which is not shown in this correlation. So that was the only thing that was supposed to be done in the exercise. So that's why we skip it. It's a very straightforward exercise, and the solution will be forwarded to all you all. So now we jump to the interesting exercise, which is so calculating this dry gas formation volume factor and the solution OGR for the gas condensate reservoir. And before we start this, I will just mention that what data are we gonna use. So what you see on this Excel sheet, we have the composition. So that these are the components, H2S to C7 plus, and then we have composition, molecular weight, and density. So this composition, this is actually the composition of the gas condensate fluid that we have in the PVT report that we sent to you all. And I can just open the PVT report. Yeah. So this is the gas. So as Matthias might have already mentioned, that we have two PVT reports that are handed over. One is the gas PVT report, and the other one is the oil. And so for this exercise, we are using the composition from the gas condensate reservoir. So the composition that comes from this table here, table 2 of this PVT report. So you see that methane is about 73.13, and if we go to the Excel file, say that's 73.13 here, and then C7 plus is about 8.29, which is the sum of all these numbers here actually. So that's come from there, and then the molecular weights. These are the standard molecular weights, and the normal C5. For C6, we have used the value from this standing cards and Prosabadi table, 84, and same goes for these densities. And then for 0.69, that's the density coming from the Karlsruhe body table for the C6 pseudo component. And then C7 plus, the molecular weight is already reported in the report, or maybe not. Yeah. So here the C7 plus molecular weight is, you can calculate the C7 plus molecular weight from the compositional data, and knowing the molecular weights that come from the capture body. So that's the C7 plus molecular weight, 188, and then 0.816, that's the specific gravity or the density of the C7 plus fraction, and it is calculated from a correlation that we will on day 4 when we will be developing the EOS model. So don't bother yourself with what's written with the comment here. So that's all with the input data, and then we have the reservoir pressure and reservoir temperature from the PVT report. And now when we are going to calculate the BGD and RS, little RS, we know that those are black hole PVT properties, and we need to have some kind of surface process to calculate those numbers. And the assumption for the surface process we are making here is that what we will say that in this gas condensate composition, which we are referring as a well stream composition. So in this composition, all of the C6 plus component will make up our stock tank condensate. So in the stock tank condensate, there will be only C6 and C7 components of the well stream. There will be nothing lighter than the C6 in the stock tank condensate, and the total surface gas will make up from the C6 minus. So all of these components here, they will make up our surface gas. So that's the very simple assumption, and usually it's a good assumption. Like we will see how close it is with the lab data that we have, and yeah. So with these assumptions, we can calculate this BGD and RS, the black hole PVT properties, and that's the objective of this exercise. So we need to calculate these are the numbers that we need to calculate to calculate the BGD or RS, or you can use like this is just to make it clear like how this BGD and RS are calculated. If you calculate these properties individually, it will be more clear how those properties are calculated with the definition that we have shown in the PowerPoint. But you can use other direct methods to calculate those BGD and RS values. So I guess I will maybe we just wait like 5-10 minutes or maybe 5 minutes so that you guys get yourself familiar with the Excel file and start doing the calculations on your own. And then after 5 minutes, I will start doing these calculations step by step with you all, and you can see the solution, and then you can we can take any questions afterwards.
Sounds good. So we'll take 5 minutes now just to try to do the exercise on our own. Just use the chat to ask any questions. All the relevant equations should be also given in the formulas and definitions. So yeah, just give us a heads up if there's any questions. Okay, so I think we'll get started. Okay.
Okay.
Very good. So we'll walk through this step by step. Bilal.
Yeah. So I guess maybe some of you have already started the exercise, and maybe have reached to the. Some of you might have reached to the end of the exercise, maybe by now. But we start with this first calculation. That's the as Matthias mentioned during this. During the presentation, that we are using a nomenclature with a hat. So hat was I didn't put a hat here because this is just a text in the Excel file. It's not an equation. So but NGG, the first one for the first letter is with the hat actually. So NGG is actually the gas moles coming from the reservoir gas phase, and here we only have the gas phase, reservoir gas phase, which is the gas condensate, which is with this composition. So if you want to calculate the surface gas moles, so we know that all the components that are less than C6, they will end up in the surface gas. So the moles of the surface gas will just be the sum of all these components until normal C5. And the composition is in the mole percentage, so we can just take the sum and then represent as the moles of the gas phase that will end up as a gas phase at the surface from the reservoir gas phase. And then for the oil, we know that the C6 plus component will end up in the surface oil or the condensate, so we just take the sum of C6 plus. So that's our surface oil moles. Now we need to calculate the molecular weight of the surface oil. And for the molecular weight, if you look at the formula sheet here, so there is this expression for you can calculate the average molecular weight, which is just the sum of product of moles times molecular weight of each component divided by the sum of moles. So if we go back here, you can use that formula. So we need to use a sum product in the Excel sheet, and sum product of the moles times the molecular weight divided by sum of moles of the C6 plus content. So that's the molecular weight of the surface oil. Seems reasonable with the number 176. That's what is expected. And for the gas condensates,
you should also, since it should be a number between 188 and 84, since you're mixing essentially up those two components.
Yeah, that's right. And now the MOG, that's the mass of the surface oil coming from the gas phase, and we know that the definition of mass is moles times the molecular weight. So we have already calculated the moles, and then we have calculated the molecular weight. So that's the mass in the pound LB mass of the surface condensate. Now comes the density, and so for the density, what we are going to use, again, if you go to the Excel sheet, so here you see the formula for the average density or the gravity, and it's again, so here what we are using, this is the formula for the average density based on ideal volume mixing. And what ideal volume mixing means is that if you have let's say if I have 1 barrel of hexane and 1 barrel of heptane, and if I mix them together in a container, then I will get 2 barrels of the mixture. So that's just what the ideal volume means. So what we are doing here, we are calculating the in the numerator, you see that it's the sum product of moles times molecular weight, which is moles times molecular weight is the mass. So we are calculating the sum of masses of all the components, which total mass. That's okay. And then in the numerator, here comes this ideal volume mixing assumption that this Zi sum of ZI/Mi. So ZI/Mi is the mass of each component, and we are dividing it with the specific gravity or the density. So this whole thing is actually the mass divided by the density, which is the volume. And we are just summing up the volumes of all the components and assuming that it will give us the total volume of the mixture, which is the ideal volume mixing rate. So we are dividing the total mass by the total volume, giving us the total or the average density. And the ideal volume mixing assumption is generally okay for these stabilized liquids where we have the components which doesn't boil off at the standard conditions. So for like C6 plus, C7 plus content for the flashed oils, we generally it's a good assumption.
Curtis?
Yeah, nothing really special. I just wanted to make a comment that in 1980, when I was working on the first paper I did on the characterization of heptanes plus paper, in the original version of that paper, I actually got the ideal volume mixing equation wrong, which one of the reviewers who didn't want it published pointed out, and I guess so. It's just a kind of a reminder to everybody. It's you can climb the learning curve on any subject, and this has been a long one for me. But these things were not taught in at least that I remembered in probably in high school chemistry, and I forgot it by the time I was finished with college. But you know, some of these are fundamental to what we're doing. And the ideal volume mixing is a very, very good approximation for hydrocarbons. So just
Good.
Yeah. Thanks, Curtis. So so we will just apply that formula, and we can see in the formula that the this guy here, MOG. So we just take this and divide it by, now we have to calculate this numerator here. Oh, sorry, the denominator. And for this, we can use the sum product again. And thanks for Microsoft Office to give the flexibility that we can add multiple arrays, and we can have 1 over some array as well. So we have so first we take the moles, that's good. Then we take the molecular weight of each component, and then is 1 over the density or the gravity, which is this guy, these two here. Okay, so now this is gonna give us the gravity, and then we have to multiply. This is gonna give us the density, for example, density at in gram per cc, and then we have to convert it into lb mass per cubic feet. And for that, we know that 1 gram or 1 gram per cc is equal to about 62.4 lb mass per cubic feet, which is the density of water. So we just multiply it with 62.4. That's 50.9 lb mass per cubic feet of the surface condensate density. So 62.4, that's yeah, we just rounded off because otherwise it's 62.366 or something. So yeah, so that's the surface condensate density, and then now we need to calculate the volume of the condensate, and that should be very easy now, because now, but that's just again the ideal volume mixing. We have calculated the density from that, and now we just take the mass divided by the density of the condensate to give the volume. And now this should be the volume in feet cube, because we are using the density in feet cube, right? So we just have to divide it by 5.61458, which is the conversion to barrels. Okay, and then the next thing is to calculate the surface gas volume. And for surface gas volume, if I think you have it in the formula sheet as well, the formula for if we have the moles, then you just use the ideal volume, ideal gas law, and there was. Do we have Matthias here, or just need to? Okay, maybe we don't have.
Yeah, the ideal gas law is in the top there.
Yeah, but yeah, you can apply this ideal gas law here, or I can show you one more thing that's there in this SP monograph. Because if we go to this chapter 3,
it is on the first page of the formula sheet.
First page. Better to use one.
The gas mixture 3.3.
3 point.
First
Yeah.
page.
Yeah, but yeah, that's the ideal gas law, right? But I'm just showing in the monograph. You can see here equation 3.27. So here you can see that if you have 1 mole of the gas, and if you take it to the surface conditions, the ideal volume of or like surface condition, meaning that 14.7 psi, 15 degrees centigrade, this much would be the volume of that gas, and that just comes from this ideal gas law. PV is equal to nRT. So we can either apply this equation, or we can just use this number 379.4 here. So we know how many moles of the surface gas we have. That's this number here, and then we just multiply it with 379.44, or was it 379, right? 144. Oh, just 4. Okay. So that should be the volume of the surface gas we should end up getting from these moles. So now we go to, and okay, so all these calculations, these were for surface gas and surface oil. Now we will do some calculations for the reservoir phase, which is only the gas phase. So now we calculate the average molecular weight of the reservoir gas phase, and again we use the same equation that we use for the surface oil, which is just the sum product of the moles times molecular weight. And then divided by the sum of moles, which is 100. So that's the reservoir gas molecular weight. The gravity is just dividing the average molecular weight with the air molecular weight, 28.97. This is also in the formula sheet.
To the bottom. There.
Yeah. Here, gas gravity from the gas molecular weight and the air molecular weight, and then we need to find out the pseudo-critical temperature and pseudo-critical pressure for the reservoir gas phase, and that's for calculating the gas Z factor from the standing correlation. So for that purpose, if you go to figure 3.7 in the SP monograph, I can open it here. 3.7 here. Yeah, so this, and then we have the gas gravity, which is 1.22, which is somewhere here, gas gravity. Yeah, so somebody.
Gas gravity is higher than.
Yeah, so gas gravity is higher than 1 because we are talking about the reservoir gas phase, which is a gas condensate, and you will see when we will be going through the report in detail, that it's a very near critical gas condensate. And near critical gas condensate, they have a lot of C7 plus content. You see here about 8.29 mole percent. It can be much higher, and because of that, you get very high gravity. With even and it 1.22 just tells you that it's heavier than air. Okay.
And in fact, you don't have to have a reservoir, like a stock tank gas, a gas coming off the stock tank will often have a gravity that's from 1.5 to more than 2.
Yeah.
Because it also contains a lot of heavier components, being at low pressure.
Yeah. Yeah, and that's something like why the stock tank gas can have a lot of C7 plus content. We can also come back to that, and we will be looking at K values.
Yeah, perfect. Very good.
Okay, so to get this pseudo-critical temperature and pressure, we use this this figure here. So here 1.22. So if everybody just use this graph 1.22 maybe somewhere here, and then we just use one of the correlation, that this straight line here. So this will give us so this line will give us the pseudo-critical temperature, for example, and which is about 535 or something. You don't need to be, or 545. Yeah. So maybe 540. That's what Marcus is saying here. So we just take that 540 Rankine, and then pseudo-critical temperature or pressure, which is about Marcus, use your eagle eyes.
My eagle eyes.
So about the 640.
Yeah.
Okay. So 640 here. Again, Marcus wins. So now, so we have the pseudo-critical temperature and pressure. Now we need to calculate the pseudo reduced temperature, which is just dividing the pseudo-critical temperature with the average temperature we have. So the average temperature we have is in Fahrenheit, so we need to convert it into absolute units. So just add the 460. You're not using all the digits, 459 point this. So 460 should be good enough here. 0.76, the pseudo-reduced temperature, and then the pseudo-reduced pressure would be taking this divided by the reservoir pressure that is already in absolute units. That's good. Oh, sorry, it should be the inverse. Yeah, both should be the inverse. So it should be the pressure or PPC, and then this should be the T or T or PPC. Okay. So now we have a pseudo-reduced temperature of 1.3 and pseudo-reduced pressure of 11.72. And now we can calculate the gas Z factor, which we can use the standing card Z factor chart. That's also in the monograph. Yeah. And here we are not applying any hydrocarbon corrections to the values, because there is not much S2S and there are very small amounts of CO2 and nitrogen. So should be okay with that approximation. Yeah. Yeah, so that's this famous standing card Z factor chart. Curtis can tell you all the stories about the standing cards, standing and card Z factor. So what were the values actually? The 1.31, so that's the pseudo-reduced temperature. Yeah, so all these lines here, we see that these are a different reduced temperature. And then we have pseudo-reduced pressure of 11.72. So first we need to find out where are we gonna use this top part of the chart, because you see that the chart has two parts. One is this top part, and then we have this bottom part. And the way we are going to decide that is looking at this PPR value, which is 11.72. And we see that we don't have this value here on this axis here. So if you have a pseudo-reduced pressure that's lower than 8, then you use this top figure. If you have it higher than 8, then we go here and find the value here and then use the lower part. And so we have 11.72, which is about somewhere here, and then we have 1.31, that's the pseudo-reduced temperature. So that's 1.3 is this line, I guess. My eyes are working. Yeah, so we can use this 11.72 here and 1.3. Yeah, so this should be, and then we will read the right y-axis. So that should be 1.32. So 1.32. That's what Marcus is saying. So we just accept that. So gas Z factor of 1.32 from the standing correlation. Okay, so once we have that, the gas Z factor, now we can calculate the volume of the reservoir gas phase. And we are assuming that the moles of reservoir gas phase is 100 moles, which is this total, that's 100 here. And so now the volume should be very simple. We can use this real gas law, PV equals to mgRT. We have the gas Z factor. So that is simply the Z factor times the moles, which is here, times the R, which is 10.73 for the unit system we are working on, which is not a value here, but we can add 10.7315. That should be good enough. Then the temperature, which is 250 plus 460 divided by the pressure, which is 7,500. Yeah, so 134 cubic feet, the gas volume, the reservoir gas volume. Okay, so once we have calculated all these things, so now what the objective of the exercise was to calculate the little RS, and now we have all the parameters to calculate the little RS. So little RS is defined as the volume of the surface condensate divided by the volume of the surface gas. So the volume of the surface condensate is this number here, which is in barrels, that's good. And then divided by the surface gas, which is this here. And then we just have to, because this is in standard cubic feet, and we want something that's in mm. So we just multiply it with exponent 6. Oh, sorry, we need to multiply. So we just, where is the gas? And then just multiply it by exponent 6. So that's 169.63 standard STB per mmSCF. That's our little RS, or the solution OGR. And then we need to calculate the BGD. And to calculate the BGD, we know the BGD is defined as the surface gas volume divided by, the reservoir gas volume, which is this one here, and then divided by the surface soluble gas volume. And surface soluble gas is this number here, BGG, which we have removed the condensate from it. So that's this number here in feet cube per SCF. And if you want to calculate the BGW, that's the the wet gas formation volume factor. So that's this we can calculate from the from this. Where is? Yeah, so you can calculate from the Z factor, Z times the temperature. Where is temperature? Plus 460 divided by the pressure, and then you have you can just multiply it with the PSC or TSC.
This equation is also given in the
Formula sheet.
Yeah.
Right. Where is that equation? You can show it to everybody. Yeah. So this 0.02827, that's a constant number which comes from this RTSC over PSC. So yeah, so we can just use that number 0.02827, and that is gonna give us this in BGW in feet cube per SCF. So just use that number 0.2827. Yeah, and you see that these two numbers are different, right? And we can calculate how much difference we have. Minus divided by yeah, so about 9%. Yeah. So that's what Curtis was mentioning, that if we use for example, if you would have used BGW to calculate the in-place numbers, then you would the in-place volumes, the gas in-place volumes would have been 10% higher than the true sellable gas volume, surface gas volume. Okay, so we have now the dry gas formation volume factor, and we have this little RS, and now we can see how close they are compared to what the lab has reported. Okay, so we have this data here that is taken from the report. The gas Z factor at reservoir temperature and pressure 1.32. You can look at it in the PVT report. We will go through the PVT report in more detail when we will be going through the lab experiments. But we can find the gas Z factor in the CCE experiment of the gas condensate at reservoir pressure of 7,500 psi. The gas Z factor is 1.32, and you see how close it is with the it's an exact almost an exact value from what we calculated from the standing correlation. So that's something we will also go through. That the standing correlation can be used as to do the QC for the lab reported gas Z factors, and usually the lab reported gas Z factors are within 1 to 3% error compared to the standing cards Z factor calculated from the standing cards Z factor chart. And here we got almost an exact value. And when it comes to the little RS, so for the little RS, what information we have from the PVT report is the condensate, the gas condensate sample that we have in the report. That's a surface recombined sample. So there was a separator oil sample and a separator gas sample recombined at the separator GOR, and the separator GOR is yes, it should be here.
Provided in the composition.
Yeah. So the separator GOR that was used for the recombination was 4922 standard cubic feet of separator barrels. Okay, and we know that this little RS, this is on a stock tank barrels basis, like stock tank condensate. And here, this is the GOR is at separator conditions. So we need to convert this GOR from separator conditions to the stock tank condition. And for that, we need the shrinkage or the formation volume factor of the separator oil. So if we go further into the PVT report, so here you see single stage flash of separator oil at standard condition. So lab they took the separator oil and then flash it to the standard condition, and the formation volume factor they got from that flash of the separator oil, it was 1.093. So we can use that formation volume factor, and then and also we have the GOR from the flash of the separator oil. So we can use these two numbers and this number here to calculate the total GOR of the well stream composition, the total two-stage GOR with the sampling separator condition. So that's what is done here actually. So you see 4922, that's the separator GOR multiplied by the oil formation volume factor of the separator oil. That gives you the GOR of the separator in stock tank barrels basis. And then you just add the GOR of the separator oil. And just taking an inverse of this, because the GOR, little rs is the inverse of the GOR in terms of unit system, and then just multiplying it with 1 exponent 6, giving you the little rs in STB per mmSCF. And you can compare this 180.79 with 169.63, and you see they are not the same, and we didn't expect them to be the same, but they are close. And the reason why they are not the same, because we have made an assumption of the surface process, and considering that all the C6 plus content will go into the surface condensate, and C6 minus goes into the gas phase.
Good.
Yeah.
Question?
Can you repeat what was 136.7 in the equation of little rs?
Yeah, that's the yeah.
Yeah.
So
Question. Yeah, very good point. So actually,
yeah, let's take a break now, and then after the break we can go through that. That's a calculation of total GOR. It's actually something that is very applicable, and at least I use it a lot myself. That formula for when dealing with and analyzing PVT reports. We'll take that as the first question when we get back to the break. But now I think everybody deserves a 15-minute break before we start again. 15 past. We'll cover that question just after the break. We good? Okay, so we'll get started again and just follow up on that very, very good question before the break. It's a very common question. It's a relevant question because the calculation in many times is not done and stated explicitly in commercial laboratory reports. So it's actually up to us as engineers to do this calculation, which is essentially calculating a total GOR, so scuffs per stock tank barrels, for instance, a gas condensate as here, from a separator metered GOR using the other associated properties provided to us. And the formula is fairly simple, and it's that the GOR total, so the total GOR is equal to the separator meter GOR, this guy right here, which is metered at the first stage right here, oil and gas rate, where the oil rate is in step BBLs, that's the volume, and the gas rate is actually automatically converted into scuffs, or many times we also, depending on how large a well is, you'll have some M's there as well. But they'll provide us with a GOR at separated conditions at scuffs per separator barrel. This GOR will always be lower than the total GOR, because from separated conditions down to stock tank, the oil shrinks because there's gas coming out of solution, which is what we try to draw here as a cartoon. And to account for this, we need to apply a shrinkage factor to the separated oil volume. In addition to that, we need to add the so-called flash factor, which is just a way to account the gas that comes out of solution of the separated oil volume. So two different ways to write this formula. It's the same formula. It's the GOR set divided by the shrinkage factor plus the flash factor. Or since the formation or the volume factor of the separator is just the inverse of shrinkage factor, we can also write it as the GOR at separated conditions, multiply with the volume factor at separated conditions plus the flash factor. And just to look at our PVT reports in the condensate example, I can't exactly remember where it is, but we see that the total GOR is 4,922 scuffs per separator barrel. That's why we have that right here. The second point is, so this is this flash of separated oil to stock tank conditions. The separator volume factor is 1.093. So here we haven't been provided the shrinkage, but the inverse of shrinkage, which is the separator volume factor. That's this guy right here. So we can just multiply that in there directly. And then from one stock tank barrel of this, I guess, condensate, we have actually released 136.71 scuffs per barrel. So that's the flash factor that we should also add here. And that is why the total GOR, so this is of course the OGR, but this formula looks like this because of this formula right here and the numbers, which is this number right here and this number right here. And for those of you who are very interested in shrinkage, I just uploaded a paper onto the SharePoint folder that we have shared with all of you, that will be dynamically updated throughout the week, where there is a paper on quantifying separator oil shrinkage, because this is actually something that we meter a lot of these wells at separated conditions, and it can actually change significantly through time. So how to actually deal with that, and just to show a plot of so this is just a well in North America where shrinkage factors every single day. So that's just the inverse of volume factors, and the associated flash factor is changing every single day. And you need to account for that to convert from separated volumes to stock tank, as stock tank volumes is what we are mainly interested in. Very good. Anything to add there?
Yeah, just one quick comment. So in the exercise, we used some kind of we use assumptions on the surface process and calculated the black oil PVT properties, but it's the same process that we're going to use when we are going to generate black oil tables with an equation of state model. But when we generate the equation of black oil tables with an equation of state model, then we will use some real process and then use the equation of state model to calculate all these volumes that we are calculating for the surface conditions, with some assumptions on ideal volume mixing and then assumptions on the surface process. So that will all be done with an equation of state model more accurately, and that we will see on day 5. But it will be the process will be very similar.
Yeah. Just to highlight that point from Bilal right here. So this is quote unquote the correct technique barrel per million, and if we pull up the wells in the software, so the gas condensate well, that's exactly the same well and composition that we have in the Excel sheet right here. This is the PT diagram of that well, and if we go into the black oil table module and look at, this is an undersaturated gas condensate, and we look at the solution GOR, or the CGR, sorry, right here, we actually see that's 181.23, which is very, very close to this value right there. That's an equation of state calculation with the same input parameters that as here. Okay. Very good. So on that, we'll just skip ahead. Next topic, unless there's any more questions. But again, that was a very, very good question, and something at least I have to do a lot for these reports in US and Canada, and I'm sure that's the same for Bilal, because that is the calculation the labs rarely do for you, at least unless you have a multi-state separated test ordered as well.
Mm.
Curtis, anything to add there, or is it okay?
No, I think it's just one more of these issues that really has to be understood. It's fundamental. Separator GORs, conversion to total GORs, how to do it, how it affects, more important for gas condensates, volatile oils. So it's an important part of the complex PVT.
Very good. Very good. And it also just iterates the importance of actually assigning a context to the volume. So separator barrels, stock tank barrels, reservoir barrels. It's very, very important to understand the context of where this volume were measured and at what conditions. Very good. So we'll take this a step forward now. So we've learned about black oil PVT properties. We've looked at fluid classification, such that we actually we understand the difference between different fluid systems. And now to maybe a very, very common and well-known calculations related to reserves is when we calculate in-place volumes, and we'll actually do that today for 3 different fluid systems: an undersaturated oil, an undersaturated gas, and some system that is actually has 2 phases in the reservoir, and we'll see how we'll deal with that as well in an exercise. A lot of the definitions that we learned so far, the different properties and whatnot, this stuff will get used for in this section. So I think we'll just step right to it. We'll just repeat 2 things. Here, this is just again defining the nomenclature: VO, reservoir oil; V, subscript O hat O, is surface oil originating from reservoir oil; V, G hat O, is surface gas originating from reservoir oil. And this one right here is actually, it looks, just one second. Yeah. So everything here is important to emphasize that this is actually some kind of complex process. Can be a 3-stage process or multi-stage process or a processing facility, the end products is going out to a surface gas and surface oil. And just repeat these formulas is also provided in the formula sheet, so I'll just remind you about that, and also given further down in the slide deck. But just for all of us to repeat the oil in place and gas in place formulas. It's essentially for oil in place is the reservoir volume of oil divided by the oil formation volume factor. I, that's important, so we're talking about the initial oil formation volume factor. And when we're talking about the original gas in place for oil reservoir, again, we use the subscripts O and G actively here. So even though we're talking about the original gas in place is originating from reservoir oil, and that's simply to take this initial solution GOR, so initial, and multiply with the original oil in place. On the gas side, it's the same. VG is reservoir gas. VO hat G is surface oil originating from reservoir gas, typically what we call condensate. And VG hat G is surface gas originating from reservoir gas. And that's also just a repetition for that. When it comes to gas reservoirs and when we talk about in-place volumes, we learned that the original gas in place from reservoir gas is the reservoir gas volume divided by the dry formation volume factor of gas and the initial one as such. So here is a lot of subscripts. It's dry, that's important. We learned about that earlier. And the I there is for initial. And the NG, so the original oil in place, original condensate in place from the reservoir gas is simply the original gas in place multiplied by this RSI, which is also for initial. So that's the solution solution CGR or the vaporized oil ratio. Again, also many places denoted RV. One thing that I think is not that much communicated is that you can actually almost get you can get a equivalent formation volume factor for oil, so like a BOI for a gas condensate reservoir. And the way to do that is that you actually take this dry formation volume factor of gas and you divide it by the little r RSI. Such that you get a unit of reservoir barrels per stock tank barrels, which is the same units as the BO, which is very known. And the nice thing about this formula is you can apply it in the exact same manner as you would for a oil reservoir. You would do the hydrocarbons in place, and you would divide it by essentially this number right here. Just to show an example of that again, back into our software, we see that for the gas condensate well that we're also have a PVT report for, we have the this is the gas expansion factor. That's just the inverse that we'll get to of the dry formation volume factor and the solution RS. And you actually, if you take the BGD and divide by little RS, you get this total formation volume factor right here of 3.883, and that's just this exact formula right here that we see on the screen. When we produce from a reservoir, and we're talking about a producing GOR, the gas volumes that goes above the line right here can come both from the reservoir gas phase and the reservoir oil phase, and similarly the same goes from below the line right here when it comes to oil, reservoir oil, and this is the oil volumes. And as we talked about, depending on what fluid system you're in, the producing GOR will and may change. But if you're producing at a constant composition, it will be constant. So what we'll do now is to do with a few of these items introduced, we'll actually just do an exercise or a range of exercises to demonstrate some of these things, communicate the importance, and hopefully for those of you who haven't seen this before, we can also learn the quote-unquote geologist BO and the applicability of that. So the goals here is to make calculations with fundamental black oil PVT properties, understand the difference between producing GOR and solution GOR, and also understand the meaning of this geologist BO. So the first exercise that we'll do is related to the initial producing GOR formula for different fluid systems. So now we'll link a lot of different things, right? We have defined all the fluid systems. We have talked about the different properties related to each fluid system. And what we'll actually do now for these 4 different fluid systems is to simplify this formula above to make it relevant for a dry gas, a wet gas, a gas condensate when it's producing at pressures above the saturation pressures, and a black oil when the pressure is above the saturation pressure. So we'll give everybody 90 seconds, I think, to sketch out this at home, and then we'll go through the answers of this exercise in 90 seconds. Okay, and feel free to ask any questions in the chat if that's there are no questions. Very good. So just simplify these formulas. Remember what's the characteristic of a dry gas reservoir, same with a wet gas reservoir, and condensates and black oil. Okay, so what we'll do now is to go through the answers, and I think we'll start with dry gas, and people can write in the people that would like to guess or would like to speak up what or how would this formula look for a dry gas reservoir? Any guesses? No guesses? So we can just go through the solutions, I guess. So for a dry gas reservoir, then there's no condensate produced at surface. So these guys goes to 0, which means that the producing GOR goes to infinity, or the ZGR is, which is the opposite of this. So the producing CGR, which I think is like small rp, is 0. For wet gas, however, we will have no reservoir oil volume. So both of these guys that we see here will go to 0. But we see that the producing GOR will simplify to VG hat G over V hat G, which is just the inverse of the solution CGR. An exact same argument goes for gas condensates when we're producing at bottom hole pressures above the saturation pressures. It will simplify to the producing GOR initially will be the inverse of the initial solution CGR, while for a black oil system, it will simplify to be the same as the solution GOR. Okay, so I hope that everything there is clear. What we're going to consider now is 3 different cases where we're going to calculate the oil in place, a few oil in place volumes and some interesting things with these cases. But there's like made up cases, and we're going to treat the entire. We're going to treat the entire volume within these reservoirs with a constant volume or constant composition assumption. So here we have a total fluid composition, but we actually are 2 phases in the reservoir. In this case, we have a single phase reservoir gas in this case, and we have a initial reservoir oil in this case right here. And the thing that we just saw is that the producing GOR simplifies to the solution GOR when the bottom hole pressure is above the saturation pressure for an oil. And something similar happens to a reservoir gas where the producing GOR simplifies to the inverse of the CGR. While when we're dealing with a 2-phase system, the producing GOR at surface will be somewhere in between the lower bound, which will be the solution GOR of the oil, and the inverse of the solution CGR, which is of the condensate. Very good. So what we're going to do now is to do this exercise. So there's 3 exercises coming now quickly, and then. We're going to do all 3 of them, and then we're going to go into K values and flash calculations after that. This should be a fairly straightforward exercise. The first thing is to calculate the original oil in place, the original gas in place, and the recovery factor of surface oil for this case. Well, we'll give everybody a few minutes to do that.
Gerard has a question.
Yeah.
Gerard.
Is there a question?
Yeah, Matthias. Just a simple question, and I came across this last week. From Wheatstone perspective, we know there has been quite a lot of technology advances in the last, 30 years in terms of sampling. When do you see that fields started not to be mistaken of volatile oils to gas condensates due to the advance in acquisition? I mean, when I look at the field in the 80s, I know that it could be highly misleading what they thought. But when I look at a field today, it's a lot harder, let's put it that way, because of technology development. So when do you define that line? Do you have a rule for that?
That's a good question. Curtis, you've been around since the 80s. Maybe
the draw the line between.
Yeah, to draw the line between when did you see that the industry stopped making mistakes or confusing volatile oils with heavy condensates? Was due to a technological breakthrough, or is it something that is more in the process, how we deal with samples?
Yeah, so I'm not sure that there needs to be any real distinction, because quite a few people have shown the last 10, 15 years that, whether you call the fluid a near critical oil or a near critical gas condensate, rich condensate, a volatile oil, the labeling really has very little to do with the performance and development strategy. It's So I'm not quite sure how you maybe see the labeling being important, or maybe you're just saying, when did the industry realize it wasn't important?
Yeah, that's another way to put it. No, because
Yeah, I think that's probably the most important thing. Is there's several publications that showed this, and I think it's just, it was a gradual acceptance that the labeling had very little to do at all with the way you would develop a particular reservoir, what it would be called. Now, ownership is a different thing. Some places in the world, if it's a gas condensate or a near critical oil, near critical condensate, the ownership of the stock tank barrels is different.
yes.
So there, but that's more like a political, legal definition. In terms of reservoir performance, strategy, development, essentially you don't see any, there's no demarcation between being an oil and a gas in any performance metric. I think it just became understood after a number of publications, maybe 5 or 10. It wasn't like aha experience.
Okay. Yeah, thanks. Because I noticed educational wise, we are being educated, right, to have to say what it is, and it's not necessarily important.
No, only when it's a political, contractual, not from a pure engineering point of view. No, not at all.
Okay, thanks.
Very good. And I think even it's probably safe to say, even with modern technology and considering all these studies we've done in the States, Curtis, looking at all the PVT reports there and their critical fluids and whatnot, they're it's hard to deal with near critical fluids in the first place in the laboratory. There's also uncertainty to that, which even the newest technology and expertise and knowledge and whatnot is struggling with, right?
Yeah, I mean, it's definitely difficult to experimentally to get, let's say, consistent, accurate measurements, but that's been done and can be done. So it's, yeah. So, I mean, it's a very inefficient process, recovery process from a depletion point of view, both on the gas condensate and on the volatile oil side. So, because it's almost all of the stock tank barrels being recovered are being carried in the gas phase, even if it's an oil. If it's near critical oil, you drop below the bubble point and bang, it becomes essentially a rich condensate reservoir, and all the stock tank barrels you're making is being carried by the gas phase. So, yeah.
Very good. So I think we'll jump into this exercise, and if there's any other questions, just fire away. The exercise is we'll start simple, and it's going to get harder in the second exercise, and then I'm impressed of the people who managed to do the fourth exercise. But this is the oil in place calculation. So calculate the oil in place and gas in place, and for these with these assumptions and the recovery factor. And here we have actually provided the hydrocarbon pore volume in terms of reservoir oil. So that should make it simple for folks. So we'll give everybody a couple minutes for that. And Okay, so the answers for the first exercise should be given here on the slide in front of us. We have the original oil in place is the hydrocarbon pore volume divided by the formation volume fraction of oil. And then we have the original gas in place is just the original oil in place multiplied with the solution GOR, which gives us 20 BCF. And the oil production that's forecasted to 500,000 barrels gives us a recovery factor of surface oil of 500,000 barrels divided by 10 million barrels, which gives us a very low recovery factor of 5%. So this is also like an unconventional type of reservoir, where these type of low recovery factors are common. Good. Going into yeah, we'll actually just do this this exercise right here. Also give everybody a few minutes for that, and then the boss on the side here, Bilal, told me to speed up to be able to cover the last topics for today. So also here, give everybody a couple of minutes to first of all calculate the original gas in place, and then the original oil in place, and then this BGD over little rs value right here. And again, the hydrocarbon pore volume is provided. We good? So it's not. It should be. Oh, sorry, 75. 2.5. Okay. So we should have gotten the original gas in place to be around 33 BCF, and the original oil in place to be 2.5 million stock tank barrels, and then this BGD of a little RS gives us this quote unquote BOI for gas condensate, which is 8 reservoir barrels per stock tank barrels. So with this, you can actually just check the calculation in number B by doing the hydrocarbon pore volume of the reservoir gas divided by this number 8, and you get 2.5 directly spitted out. So that's nice and convenient, and can be applied for a kind of consistent. And we'll look more actually at this later throughout the week when we talk about black oil tables and extrapolation and these things. Very good. This exercise D we need to skip, but let me know if any of you try to do it, and we can discuss the answers. It's really interesting. So the assumption here is if you produce from a reservoir where you produce a reservoir oil and a reservoir gas phase in this particular ratio in the reservoir, and you should try to, and each of the phases has these associated properties, and you're supposed to calculate the producing GOR, which is cool, and the producing GOR should be between the inverse of RSI and the large RSI. But we'll skip this for later. There's also another exercise associated where you exercise 3 is exercise 3 the
assumes no gas cap, right?
Yeah, or depends on what if exercise 3 is exercise D, then so just assume that what's flowing in the wellbore is so what's flowing in the wellbore is 20% reservoir oil and 80% reservoir gas, and that point in time you're supposed to calculate a total producing GOR.
So you have a gas cap and an oil rim, and then there is 80% of the free gas phase flowing and 20% of the free oil phase flowing.
That's one scenario, and it can also be that just the saturations at that point in time is 20 versus 80%. So it really doesn't matter how we interpret that. The only important thing is what's flowing in the reservoir into the wellbore is 20% reservoir oil and 80% reservoir gas. We're supposed to calculate the total producing GOR. Just let me know if any of you do that and would like to get the answer to that exercise. And a little bit similar, the exact same exercise. The only difference is that now, since we typically know the producing GOR, and you can assume here a producing GOR of 10,000 scuffs per barrel, then what is actually the relative oil and relative gas volumes, which is more or less the saturations in percentage. And for that exercise, you can use these equations as well, and do that at home. We'll send this out. Very good. Before we'll jump to the next topic, which is KVALs, I think, and flash calculations.
EOS model.
EOS models, yeah. We can just mention this quickly. Is if you like to make your life simple, or I like to use these formulas myself, such that you can actually calculate oil in place and gas in place with only one, or I guess two equations. You can use the oil formation volume factor, the total oil formation volume factor, and the total GOR for all reservoir fluid types, whether it's two-phase saturated, single-phase saturated, unsaturated, and whatnot, where the total oil formation volume factor is defined as such. So it's a saturation weighted average, which you'll see when the saturation of oil is 100%, it will simplify to be BO, which is what we like to have. And when the SG is equal to 100%, it will simplify to be the BGD over little RS that we just talked about right here. And that also for reference, the total formation volume factor we see here for the gas condensate well in the software provided, and also for the oil well, that's the exact formula right here. Similarly, on the gas side, we have a saturation weighted version of that as well for total oil formation volume or total GOR, which for SO equal to 100% equals the solution GOR, and for a pure gas reservoir, you'll have the inverse of that, which is 1 over little RS. That's again the property that we see here, the total GOR. That's this number right here. Very good. So now we talked about the black oil model. We talked about in-place volumes. We'll talk about the equation of state model now. Introduction. Yeah, and this is just an introduction to give more or less a broad overview. And since I see we're a little bit behind on time, we'll try to speed it up a little bit. But as I mentioned, these black oil tables that we use today, they're typically derived from equation of state models. And this is just an overview of that as an introductory overview of equation of state models. And this, at least from a high level, summarizes equation of state models in the petroleum industry, where we use 2 different types of equations most of the time, not probably 99.99% of the time, which is the Peng-Robinson equation of state and the SRK equation of state. If you ask someone to send you an equation of state over email or want to look at an equation of state like physically in some kind of format, what it actually will look like is 2 tables with a set of component properties and a set of binary interaction parameters. The component properties is the component name, so that's methane, for instance, the associated molecular weight, the critical pressure, critical temperature, something called eccentric factor that we haven't talked about yet, that we'll talk about later, the volume shifts, and also some critical C factors that's we'll also talk about later for viscosity modeling. Just to make it hands-on and practical, you can look at the equation of state that we're using in this course, which is first of all an SRK equation of state. So that's one of the 2, the one down here, Svavel-Rödlich Kwong. And we see there's 1 table with component properties and 1 table with binary interaction coefficients. And we have everything from H2S, nitrogen, CO2, C1 up to C26 plus, which is a long component. Again, the inputs to an equation of state model is the 3 parameters important for PVT, composition, pressure, and temperature. And with that, we can predict the phase volumetric behavior. When it comes to where we're going to actually create an equation of state, we first need to do sampling, which we'll talk about later, lab testing, create some lab data that we use in some kind of equation of state modeling software, PVT Sim, PVTP, phase comp, WinProp. There's several examples of those. We need to do some tuning of that equation of state, and then the tuned equation of state model can be used either to create tables, or that's black hole tables that we just talked about, or you can use them directly into simulation, the equation of state, or you can use a derived product of that into what we call EOS model utilization. So utilization engineering with the equational state model, fluid model. That can be material balance equations, reservoir modeling, well simulation, process facility design. When it comes to equational state calculations, we have here we have a cartoon of a total fluid mixture at some pressure and temperature, and we would like to know the following. So given an overall fluid composition at a given pressure and temperature, determine the number of phases, single or two phase or three phases in some cases, and determine the relative amount of equilibrium oil and gas, and then determine the composition of the equilibrium oil and gas, and that's determined by the K values, which is what we talked about earlier. So one very key, of course, also to determine the essential fluid phase properties of each phase. So that's volumes and densities. And we can in many ways say that one of the key, I guess, objectives of an equational state, or to use an equational state, is to generate K values. So it's has like an internal K value generator for us at different conditions that we can utilize for engineering purposes. So equational state models are simple equations relating pressure, volume, and temperature, and an equational state model accurately describes the multi-phase thermodynamic equilibrium of a multi-component system, as well as the PVT properties of any given phase. So combined with a mass material balance equation, Rutherford Rice, that we will talk about later, the EOS model gives us the equilibrium phase split of multi-component fluid mixture. And this is just a overview of where equations of state are actually used, and that's for a wide range of different applications related to processing, production, and reservoir.
Okay, so I think we can start this new topic, which is gonna be one of the last topics we are gonna cover today. The equilibrium ratios of K values, and this is gonna be this is going to be one of the most fundamental concepts that we are going to use when we are going to talk about equational state model development. So we will just jump into the topic. K values, how we define K values. So a K value for a given component I is defined by the ratio of how much, or like the mole fraction of that component that exists in the vapor phase divided by the mole fraction of that component exists in the equilibrium vapor phase. And we will see in the coming slides like on what factors the K value depends. But what K value, the magnitude of K value represents is actually the preference of a given phase to be in the vapor phase. So if you are comparing the K values of two components, like for example methane for example normal pentane, if you see that one component has a higher K value compared to the other one, it means that the component with a higher K value would like to be more into the vapor phase compared to the liquid phase. Okay, and yeah, so that's we are gonna see it in the coming slides. And the K value is always positive, so it has to be greater than 0, but it could be greater than 1 or less than 1. So that depends on which component we are talking about. Yeah. So there was supposed to be an exercise where you were supposed to draw K value versus pressure, but we are skipping this exercise because we are going to talk about this plot in the coming slides. So we are going to talk about how this plot looks like and why it looks like the way it is supposed to look like. So Yeah, so again here, this K value definition, this is the figure here on the right. This is coming from the SP monograph, and we have just mentioned the different lines representing the different components. So you can see, for example, methane. So these are the K values drawn with the pressure. So this was the exercise that you guys were supposed to do in the previous slide. So we have this this is on a log scale. So K values on the log scale and pressure on the log scale, and this is the K value of 1, and you can see the different components, like you have methane, ethane, propane, butane, pentane, and n-hexane. So for a constant pressure, you can see methane has always a higher K value compared to, for example, ethane, propane, which means, for example, if I compare methane versus ethane, it means that methane has higher tendency to be in the vapor phase for at any given pressure compared to ethane or propane and all these heavier. So as the component gets heavier, it has more tendency to be partitioned into the equilibrium liquid phase compared to the gas phase. And this shape of the K value, like why the K value is decreasing with increasing pressure, and then all the K values are converging to one pressure, where the K values of all components are equal to 1. That's something we are going to talk about in the next slides. You have a question?
Corrado, you have a question?
Yeah, no, it was yeah. I mean, you're gonna talk about it. Why do you have a positive slopes on the components before reaching 1?
Yeah. That we are gonna talk about in the coming slide. Okay, and if you have only one component, single component, then the K value is always equal to 1, and that is at the vapor pressure of that component, because it's the same component that's partitioning into the vapor phase and the liquid phase. So the K values are not relevant for pure components. They are only relevant when you have mixture of different components, and then we talk about the K values. Okay, so in order to understand the behavior of K values versus pressure, we actually have divided this plot that we are looking here on this slide. We have divided into two parts. The first one is the low pressure range, which is generally 10,000 or 1500 psi, and also this plot, this log of Ki versus log of pressure, this is plotted at a constant temperature. So you have the temperature being constant, and then we are only changing the pressure and see how the K values of the different components vary. And so now you see, so at low pressures, we have 3 components. So the top one, you can say that's, for example, methane, and that's the lightest component. Then in the middle, we have some intermediate component, let's say, for example, hexane. And then this is, for example, a very heavy component, C20. And that's what you expect, that the K values at all pressures for methane should be higher than, for example, C6, and C6 K values should always be higher than, for example, C20, because the lighter the component, it has more tendency to be partitioned into the vapor phase. Okay, and so that's kind of our low pressure range, that's less than about 1000 or 1500 psi. And what you also see from this plot, that these K values for a given component, when they cross the pressure axis, which is coinciding with the log of Ki equals to 1, so you will see that these K values for the different components, they cross this pressure axis at 2 occasions. So it's also, if you go to the back, if you go back here on this figure, you see that, for example, ethane is crossing the K value here, and then it reaches, and all the K values, they again cross this K value equals to 1 at 1 pressure, which is where they are all the same, which is equal to 1. But before this pressure, which is special pressure, and we will talk about this, but before that pressure, these components, they cross this K equals to 1 at different pressures. And this pressure is termed as the vapor pressure, it's a pseudo vapor pressure. Actually, it's not the exact vapor pressure of that component at that temperature, and it is affected by the binary interaction parameters in your equation of state model, which Matthias just showed. That's just one of the tables in your equation of state model. So it's a pseudo vapor pressure at a given temperature, and that's different for the different components. So, for example, if you have you see that ethane, it has a higher vapor pressure for at a given temperature than propane, then butane, and then pentane has vapor pressure that's that will be on the left. That is not shown in this plot. Further lower than the butane, for example, and then hexane will have much lower vapor pressure. And what you also see from this plot, that all these K values at low pressures, they are linearly decreasing. And that's what we expect, that as you increase the pressure for any given component, it will have more tendency to go into the liquid phase at low pressures, right? It will try to be compressed and then form the liquid phase. So that's why as we increase the pressure, the K values of all components decrease. And they at low pressures, you will see that all these K values, they actually linearly decrease. And if we plot the K values on a log scale, then you will find out that the slope of these K values is equals to 1, -1 if we put a negative sign. And that's because the K values at low pressures, they can be approximated by this expression here, okay, which is the K values. The K value of a given component is given by the vapor pressure of that component at the given temperature divided by the total pressure of the system. And this expression is the expression that has come from this Dalton's law and Raoult's law, the combination of the two. So that's why the K values at low pressures, they have very simple behavior, all of them decreasing with a unit slope, and they cross this pressure axis at the point which represents the vapor pressure or the pseudo vapor pressure of that component at the given temperature. Okay, and yeah, and also because these K values at low pressures, generally if we talk about the practical applications, so these K values are only relevant for your surface processing where the temperature is also lower. So when we talk about low pressure K values, then generally your temperature is also lower. And yeah, so the low pressure K values, they are approximated by this Raoult's law and Dalton's law. And at this low pressure range, the K values are not much affected by the total composition. So if you have a producing composition that's an oil-like composition, you have a well stream composition that has, for example, a bubble point, versus a well stream composition that has a dew point, for example. Matthias showed in the video that well stream composition can be a bubble point or dew point, for example, in unconventional resources, depending on what you are producing. These K values, they will not be much affected by the total composition that you are producing. It will mainly be function of your pressure and temperature. Okay. And if we have accurate characterization of the vapor pressure of individual components, it means that you will get accurate K values, which means accurate. What does accurate characterization means? It means that all the component properties that you need to calculate the vapor pressure of the component, which means that you have TCPC, eccentric factor, for example. If those component properties are accurately characterized in your equation of state model, it means that the K values that you will get from from the equation of state model. And also the binary interaction parameters are also relevant here because that will affect your pseudo vapor pressure. If your equation of state model is very well characterized, you will get accurate K values, and that will be independent of your compositions. So whatever your composition, whatever composition you will input in your EOS model, you will get accurate K values at low pressure.
Yeah, one question. We many times in reservoir simulation to mimic the process, we use K values, right? How much difference do you find in countries like Norway that you might have a platform producing with a range of, let's say, 15 degrees from summer to winter time?
You mean how much is it gonna affect the?
Yeah. So for example, when you have platforms that they produce from subsea, and the temperature really matters all the way going into the process, then you have changes in between the winter time and the summertime. Now, what you have is a Ki, that K values that are produced at a certain pressure and temperature for the process, but that changes all the time.
Yeah.
How much error do you think we're talking about when we take that approach?
Where you don't take into account the temperature variation with time?
Or you don't take into account, yes, the temperature variation with time, right? You just
assume it's constant.
Yes.
Right.
Yeah. May I, Curtis, on this?
Sure.
So it's a very good question, and it's very relevant for because here you're talking about temperature changes being one, and many places in the world it changes with the seasons, which is a very good point. And in addition to this, making it even more complicated is that you also have a separator pressure that might change depending on what drawdowns you're producing at and whatnot. And in some areas the changes are more dramatic, and if the changes themselves are more dramatic, of course it's more important. But it's also related to the fluid systems, where leaner fluid systems tend to be much more sensitive to these type of changes. So actually, in terms of reading, we have one paper, which was the one we talked about earlier in forms of separator oil shrinkage, and another paper that we presented now at ATCE, where we do what we call CGR normalization, or what we do is actually converting oil rates into a constant set of separator conditions, even though in reality it was produced through the same set or through changing separator conditions. And this exercise right here and that paper shows for a range of different fluid types, and also, as importantly, the separator, a range of different separator conditions, so temperature and pressure, when it is important and not. So I'll attach that paper to the handouts, and we can also talk about it more offline if wanted as well. But the short story is, and I think what we found there was a higher separator pressure, and the changes in pressure was somewhat more important than the changes in temperature, just because the potential changes in pressure is seen in the field, at least, is much larger than the temperature changes.
Okay. Yeah. Thanks. Yeah, and if you can attach those papers, thanks everything. Thank you.
And I can just add one more comment on this. Like if the variation in temperature is only at the stock tank conditions, and the separator temperature and pressure, for example, are not varying much, then you will not see much effect, because then it will be only affecting the K values at stock tank conditions, and there are not many moles that you end up getting at the stock tank condition. So you do most of your processing at separator conditions. But if it's only the temperature that's changing at stock tank condition, it's not gonna affect too much the total system composition that you are producing, because the number of moles that you end up getting at the stock tank will be very small.
Yeah. Okay. Thanks.
Okay, so we are talking about these K values at low pressures, and the characterization of the vapor pressure. If that is accurate, the K values will be accurate. And these component vapor pressures are well known for these lighter fractions, like the pure components we have, C6 minus. And for C6 plus, we need to have a good characterization, at least reasonable characterization for these component properties, TC, PC, and TB in the equation of state model to get reasonable vapor pressure with an equation of state model. And initial EOS model, it is developed like in an initial EOS model, meaning that it's not tuned to any PVT data, but it is generated with some proper C7 plus characterization work that we are gonna see on day 4. That equation of state model is generally reasonable in predicting these equilibrium phase compositions and K values at low pressures. Okay, now if we look at this K values at higher pressures, then what we see actually that these K values converge to one term as which is actually called the convergence pressure, represented as PK. And here the K values of all components are equal to 1. And this convergence pressure, it has only physical significance when the temperature that we are using here is the critical temperature of the mixture. So if it's the critical temperature, then the convergence pressure will be the critical pressure of the mixture that we are using to generate the K values. And what's special about this high pressure K values is that the K values doesn't only depend on pressure and temperature, but they also depend on the convergence pressure. And the convergence pressure itself is a function of the composition and of course the temperature. So if you have a different composition being produced, a gas-like composition or oil-like composition, this convergence pressure is going to change, and all the K values at this high pressure is going to change, but the K values at low pressures will not have much impact due to the compositional changes in your system. So what Curtis usually like to call this high pressure part as shape of the nose, because in a classroom, like it looks like this is not a very well drawn picture, but if you look at this, for example, this figure that's actually drawn from yeah, so this is from the monograph, and I think the data used here is from an equation of state model maybe. So here you can see it looks like a nose. And why he generally like to call it the shape of nose, because if we have like 10 students in a classroom, everybody will have a different shape of the nose. Like my nose is different than Matthias, or Matthias has a different nose than Marcus, and Marcus has different than his dad. So everyone will have different shape of the nose, but this low pressure K values, that doesn't change with the composition. So if I have an equation of state model, and if I'm producing, for example, fluid in some part of Norway, so like for example one field in Barents Sea, and I'm also producing one fluid that's, for example, from a field in Saudi Arabia. So the decompositions of those fluids will be very different, but if the fluid type, like the relative aromaticity, paraffinicity, is similar, meaning that the component properties are similar, then the K values at these low pressures, they will be very similar for the different fluids, independent of what composition you are producing. So I don't know if I have explained that shape of the nose concept very well, Chris, but you can comment if you want here.
Well, yeah, I mean, how much it looks like a nose, I'm not quite sure. But the point is that it's a very unique characteristic to the fluid system, and every reservoir will have a different, high pressure shape, different convergence point or pressure, and it may vary within the reservoir if composition varies within the reservoir. So. And then the low pressure behavior is essentially unique to pressure and temperature. So,
yeah. Okay, and these high pressure K values, they are generally relevant at reservoir conditions where we have high pressures, and low pressures, they are generally relevant for surface processing conditions. For high pressure range, the correlations are not good enough. So at low pressures, we have correlations in chapter 3 of the monograph, and those are generally reasonable for predicting K values at low pressures. But at high pressures, the correlations are generally not good enough, and we need a very well-tuned equation of state model and the relevant composition to get the reliable estimates of the K values. So these two components of high pressure K values, like meaning compositions and equation of state models, these will be discussed on day 2 and day 3. And we will be talking a lot more about these K values during those days. There was this concept of retrograde condensation, and when Matthias was talking about little RS, that it was going to a minimum at certain pressure and then going up. So we can explain that with the help of now K values. So if look at for example gas condensate, you see that it has a liquid dropout look like this. It has a condensation and it reaches to a maximum, and then it has a vaporization. Same can be seen if we plot this little RS, that the little RS or the OGR starts to decrease as the condensation happens, and then it reaches a minimum, and then at low pressures it starts going up. That's the vaporization phenomenon. And if you want to explain this behavior, we can look at how the K values are behaving with respect to pressure. So that's the convergent pressure, for example. And here we have like for example, I had 3 heavy components, for example. Here will be our dew point, somewhat less than the convergence pressure. So here we will have single phase, a gas phase. And then as we start, you can see from the K values that as we start decreasing the pressure from the dew point, you see that the K values of these heavier components, they are decreasing. Okay, and decreasing K values means that all these heavier fractions, including this very, very heavy fraction, it tends to go into the liquid phase. So when these heavy fractions tends to go into the liquid phase, you start getting this liquid dropout. So you start forming liquid, and then you see that each of these components has a minimum on this K value plot. And after that, they start increasing again, meaning that they start going back into the vapor phase. So that's why we start seeing this vaporization again. And this minimum here, the K value minimum is different for different components. So for example, the minimum of the very heavy fraction, it may be at lower pressure compared to this component or this component. That's something you can also see from this figure, which is more, because that's like a cartoon. But if you look at the figure from this mono, Yeah, so you can see, for example, from this figure that hexane has minimum somewhere here, pentane, and then butane. So there, it's different for the different components, right? Okay, so I think this was all about the K values that we wanted to talk about today. And now there is a an exercise, and that's calculating the K values of calculating the K values using this standing correlation. So if I just show it on the, where is the information?
Sheet is it's in the, just to go to Boxit read.
Okay.
And it's up there, the first one.
Yeah. So what we are gonna go do in the exercise is, yeah, so this is from chapter 3 of the monograph, and all these snapshots taken. And in chapter 3 of the monograph, we have these different correlations for K values, and we are going to use this standing low pressure K value correlation, calculating the K values as a function of pressure. And if we open this exercise 4, that's this K values. Yeah, K values and flash calculation. And yeah, so what we are gonna do here is we're gonna calculate the standing K values at 100 degree Fahrenheit and 300 psi a separator pressure. So these are the separator conditions we have from this gas condensate PVT report that we have looked at it earlier. And yeah, so these are actually the sampling conditions of the separator oil and separator gas samples that we have in that report. And we are going to calculate the K values. So to go into this and on this formula sheet, you see that the K value is a function of separator pressure, and then you have these two A0 and A1 coefficients, which are again given here, and these are the function of pressure. And then you have this Fi term, which is the function of Bi, TBI, and the temperature. And Bi and TBI values for each component, that's given in, it's not here, but that's given in the monograph. So I can just quickly show. Chapter 3. Yeah, so that's this table 3.3. And so standing has given the BI and TBI value that should be used in its correlation. So that's written here. And then for the C7 plus fraction, which is a pseudo fraction, standing also has given the method to calculate the B of the C7 plus and TB of C7 plus from the information of N C7 plus. And this term NC7 plus is calculated from the pressure and temperature information. So NC7 plus it represents the carbon numbers in the C7 plus fraction.
Kind of an average carbon number of the C7 plus.
Yeah.
Whether it behaves like a C12 or C16.5.
Yeah, so I think it should, the correlation is straightforward. So And then we are going to calculate Fi, and then this is just the log of KIP. So let's just do it now. Yes. So it is 1 over. Okay, US. 1 over the separator pressure times yeah, so that's the exponent times A0. So that's the exponent times A0. So A0 is already calculated here. And then plus A1 times Fi. That should be here. And then we just need to fix all the formulas so that they don't get messed up when we change. And then Fi is Bi times one over the boiling point minus 1 over the temperature that we are looking. And that should be in Rankine is okay. We can just use this. Yeah. Okay, and then we just drag this. So this doesn't work. And then here we just calculate log of K values times the pressure. Okay, and then that's gonna give us this log of KIP from the standing correlation. And yeah, and on this plot here, yeah. So what you guys were supposed to do is because here this we have calculated the K values at 300 psi and 100 degree Fahrenheit. So you are supposed to do the same exercise by just changing the separator pressure, keeping the temperature constant, and calculate all the K values. For example, for C1 or methane, and then change the temperature 200 degree Fahrenheit or the same pressures, again calculate the K values. And that is to make this plot here to see how the K values at these low pressures change as a function of pressure and temperature. So I can just show it in the solved version how the plot looks like. And you can do it at whenever you have time. So if you generate those values from the standing correlation, what you will find out that this is the 200 degree Fahrenheit, the blue line, and then the black line is from the 100 degree Fahrenheit. So that's we have already seen how the K values changes with pressure. So they decrease as you increase the pressure, and with the temperature. So as you increase the temperature, again the K values increase. So higher temperature, higher K value, higher pressure, lower K values. And you can also see from this line that the slope is equal to -1 on the standing correlation. So yeah, so this was the exercise, and then if we look at this plot here, KPF plot, for example, what you will see that if we plot log of KIP versus FI that we have calculated here, so this column and this column here, so this actually looks like a linear relationship. And from the standing correlation, and this is used to do the QC, the equilibrium QC of the separator sample. So if you have separator oil and separator gas samples, we have the compositions XI and YI from the separator oil and separator gas. Then we just calculate those K values from the separator lab data, and then just plot that data on this plot and see how close it is to this straight line. And that's called this Hoffman QC, and we will look at it after we will finish this fluid sampling section tomorrow. So yeah, we will just see how so that's this lab data QC here on the same Excel sheet. So we will use the same Excel sheet for multiple exercises now, and you will see how, like, when all these puzzles will be joined, you will see how useful it is, all these concepts. Okay. So we have 10 minutes, and we have this flash calculation. What do you suggest? And because there is an exercise associated with it, right?
Yeah. I think we'll probably save this for tomorrow morning, this exercise. And then if there's any questions at this point related to anything of what we went through today. So hopefully it'll be fun throughout the week to see how all these things that we learned about today will be relevant and also useful when we're going to talk about equations of state and how we'll tie it all together. And on Friday, when we are actually using the equation of state for creating value for the companies that we work with. I don't know, Curtis, do you have anything to add when it comes to everything we've gone through up until now?
No, it's not really. It's a lot of there are a lot of concepts that is for some very familiar, for others it's refreshing what they had a long time ago. As the course goes along, hopefully the different pieces of the kind of puzzle will become clearer how they link to each other, and you'll get this clearer and clearer picture. There's just a lot of concepts that have to be gone through to get to the more advanced methods and that we're approaching tomorrow and the rest of the week. So some review is necessary. So some of this is just like trivial for you. Apologize for that. But it's I think it's good to get everybody on the same location for the rest of the week's work. Otherwise, I'd recommend, if you have time and can go through some of these exercises, that they'll all kind of work for you to go through and make sure you understand what was being done and so forth. It's I think is also worthwhile.
And I'll just make one last comment related to the question that Gerardo had. So we uploaded a paper now in the folder that's shared with everybody, and it's about exactly Gerardo's question. If you have wildly changing separator conditions over time, how can it actually affect the rates and the potential inconsistency of that? And this is just a paper that talks about that entire problem, and cases when it's important and cases when it's not. And here is a good example where you see the separator pressure. This is real data, so no cheating here. Separator pressure and temperature, how it changes throughout time, and this plot to the right here is the blue ones are assuming that the separator conditions are changing over time, as we see here, while the black line is if we assume that the surface process was constant through time, then this would be the CGR that you would produce at, so a lower CGR. So this is just a case to how large of an effect it can have in some cases, and these conditions, as you see here, and the fluid type is not unique. There's another example for a richer condensate at lower conditions here, where the change is not that visible, but there's some differences. So it is a function of how much your separator pressure and temperature is changing, but also a function of fluid type. So very good. So that's attached in the papers here. And I think since we just covered K values, Curtis, one thing that I've seen with for instance, your lectures versus other people's lectures is that you spend a lot of time in university and these industry courses of emphasizing the importance of understanding K values. Would you mention a couple of cents related to that, why you think it's important and fundamental?
Yeah, I mean, most of what's complicated with PVT is related to bubble points, dew points, critical points, retrograde liquid condensation, vaporization, development of miscibility, and all of those processes, compositional gradients, are controlled by the component phase equilibria. The volumetrics, basically, the direct volumetrics, densities and even viscosities are pretty much handled. At least densities are handled. If you know the composition, you'll get the densities right. The problem is finding or modeling the compositional variation with pressure, temperature, and composition. And when you're going to try to either match measured data that reflect compositional changes, liquid dropout curve, bubble point, dew point, swelling, etc., to get the match and to, in a sense, make predictions of those phase amounts and phase compositions accurate, it all comes down to getting an accurate estimate of the K values for each and every component. Some components may be important in one case than another, but the K values, and there's something that you can hold on to. You actually can understand what they are. K value greater than 1, it's that component's trying to stay more in the gas phase and go into the oil phase. It's less than 1, it prefers being in the liquid phase, oil phase, than in the gas phase. And so if you kind of know where the component's preference is to be, you'll know if it's in the reservoir, in the pipeline, or in the separator, you'll know kind of where its preference is to be, and you'll know that you'll be finding more of that component or those components in a particular phase. And of course that helps in designing separators and designing miscible processes, understanding gravity segregation, all sorts of things. So at the end of the day, it's this composition of the phases, how much of the phases, that controls everything related to production performance, recovery, rate, time, gas oil ratio versus time. So the problem is the lab doesn't measure K values, basically, with the exception of the separator condition. So you never see them in lab reports. You see things that are indirectly affected strongly by the K values. That's bubble point, dew point, liquid dropout curve. But nobody really showed you, why does the liquid dropout curve look like that? Well, it's simply because it's the heavy components, K value versus pressure. And so tuning the equation of state, binary interaction parameters. Why do we use them? Why do we need to use them? Because they move the K value of an individual component up or down. If it goes up, then the bubble point goes up. If it goes down for the heavy components, the dew point goes up. So you've got much of the tuning of the equation of state is to get these phase behavior related properties accurate. And it's nice to know kind of what you're really doing, even though you don't have direct controls of the K values, when you change EOS properties in the tuning process, that's what you're mainly changing. In fact, that's really almost exclusively what you're changing. Most software don't even show you the K values to give you an indication of what's been changed. How do the K values look after you make all the EOS tuning? So it's, for me and for what the work we do and for me personally, if you kind of understand the general behavior of K values as a function of pressure, temperature, and composition, then you can start understanding a lot of the complicated, what you normally find is complicated PVT. So it's, I don't know, it's, I think it's the best way. It's much easier to understand than the EOS A and B coefficients and BIPs and how they all interact. It's kind of the net product of all those calculations, and it's a number you can hang your hat on. You can try to really understand it physically. So anyway, that's why I've always tried to emphasize it.
Yeah. So I maybe just repeat the last few sentences. So the flash calculation, so it requires these three inputs. So the one is the total composition that we are gonna use for the flash calculation. Then we need to have the estimates of the K values, and then we need to provide the pressure and temperature at which we need to do the flash calculation. And then there's a process of flash calculation that we are going to see on the next slide. And this process gives us output of these three things. First, it tells us whether the total composition that we are using, is does it exist as a single phase, or does it exist as two phases at the given pressure and temperature? And then if it exists as two phases, then it also gives us the amounts or the moles of each phases, so the vapor phase moles and the liquid phase mole. And then it also gives us the compositions of each phase, so Yi and Xi. So Yi being the vapor phase and Xi being the liquid phase composition. So these are the main information that we get from the flash calculation. Yeah, so now we are going to see how the flash calculation is done. So what is the process? And the procedure, people usually know it as Rashford-Rice method. And Curtis, maybe you can just tell about the history, like who presented this method first, and how Rashford-Rice they use that method.
Yeah, so Rashford-Rice, I think, was in the mid-50s. The paper written is a few pages. I think Rashford and Rice worked at ExxonMobil, or what it was called back then. Actually, the first paper giving the equations that are detailed in the Rashford-Rice method were provided by Maurice Muscat and McDowell, 1949. That was the first paper in the SPE literature about using a computer for petroleum engineering applications. And it was specifically for calculating the flash equilibrium at separator conditions in order to design optimal separator pressure and temperature for primary and secondary stages to maximize the amount of surface oil being produced from a given well stream. So that was produced or published in 1949. And the interesting thing is that the fundamental equation that Bilal is going to show you was given by Muscat in a very terse way as a footnote. And that footnote was expanded into this article by Rashford and Rice some years later. And then it's become known as the Rashford-Rice method. But anyway, it's we could probably provide that paper by Muscat and McDowell. It's outlined in chapter 3, I believe, or 4 of the monograph, both methods, which are essentially identical.
Yeah, thanks, Curtis. And we will look at the equations that Curtis is talking about in this slide. So you will get to know what the McDowell presented and then how Rashford are using those equations. So, but the basic thing on this Rashford or McDowell method is that it uses material balance. So if you want to apply a material balance to the composition and the individual phases that are being produced with the flash calculation, so we can say, okay, if N is the total moles defined as N equals to the vapor moles and the liquid moles, then you can say that on a component basis, like for individual component I, the material balance will be like this. So this is the total moles of that component that will partition into the vapor phase moles. So NV is the total vapor moles and YI is the mole fraction of that component in the vapor phase. So that's the moles of the component I in the vapor phase, and that's the moles of the component I in the liquid phase. I should use this. Yeah. So, and then if you move forward and if you define this fraction FV or FG, that's the vapor fraction or the gas fraction, as the moles of the vapor divided by the total moles. And so then if you replace this term here, so if you replace NV by FV, then this ZI becomes, this equation can be written as this in terms of the vapor fraction. And then we can rearrange the equation for the XI like this. And we can call it equation 1, this equation in green. And here we have also used the Ki, which is the K values. And Ki, we already know that this term here, I cannot use the pen without the pointer. So this Ki already. Okay, I guess the PC has got some cold. So Ki is equal to, we already know that Ki is equal to Yi over Xi, so that we have replaced here. And yeah, so that's here. So Yi, we can say Yi is equal to Ki times Xi. And we also know that the sum of mole fractions of all component, either in the vapor phase or the liquid phase or in the total composition, they all should sum to 1. And then if that's true, then we can also write that the sum of the differences between Yi and Xi should be equal to 0. And we already know that Yi is equal to Ki times Xi. That's from this equation 2. So we can just replace it here. Ki Xi minus Xi equals to 0. And then this is the minimization function that we are going to use in the flash calculation. So when we will use the flash calculation, we will try to minimize this function to 0 and calculate this FV term. So this is function FV equals to summation of so because here now Ki and Xi, so Xi we are replacing in this equation here. In this equation here, we already know Xi from equation 1, so that's here. So we are replacing this Xi term in this equation, and the function becomes this. And now this function is, if we have the estimate of Ki, so we for the flash calculation, we should have an estimate of the Ki values, and we already, Zi is the input to the flash calculation. So we can solve this function for the FV and we are gonna do this in the exercise and see how that can be done. So once we have minimized this function and calculated the FV, now we can use equation 1 to calculate xi, because now we know FV and we have the estimates of ki, and we also know the zi values. When we are doing this minimization of this FV function, we can use the Newton-Raphson method, and then in the Newton-Raphson method, it needs a derivative. So the derivative of the previous function can be written like this. Yeah, so you can use the Newton-Raphson method, and we can calculate once we have calculated FV, we can calculate the moles of the vapor phase, knowing the total moles that we have used in the flash calculation. And we can also calculate the moles of the liquid phase. And we can also calculate xi. So once we know the FV, we can calculate xi from equation 1 and yi from equation 2. And so now the question is, so when we are doing the flash calculation, and I mentioned that we need estimates of the Ka values. And how do you get those estimates? So that's something we are going to discuss when we will discuss the equation of state models. So at low pressures, we already know, for example, there are some correlations that can work pretty well. For example, standing low pressure K-value correlation. We used it yesterday as an exercise, and we are going to use it, the K-values estimated from standing correlation, for the flash calculation exercise that we are going to do today. So for low pressures, K-value, you can get estimates of the K-values, but at high pressures, we need equation of state models to check for fugacities, and then so there are details that we are going to discuss tomorrow, most probably, when we are going to discuss equation of state models. Okay, and then you see here in the footnote, when we looked at this function that we are minimizing before, so this function that actually Rashford Rice provided us. So this so if you see this function here, this is the function that Rashford Rice provided in his paper, and this is the function that we are trying to minimize, and this was the paper in 1950. And what Curtis was mentioning, actually, that in already in 1949, McDowell, they provided as a footnote, they provided this function for the minimization of the, or for the flash calculation. And in their function, we have this Ci value, and Ci is actually 1 over Ki minus 1. And if you use this function for the minimization problem, it's actually more efficient than solving the function that Rashford Rice presented in their paper. Anything, Curtis, that you want to add?
Muscat with a K.
Oh yeah, sorry.
Yeah, that's okay. Yeah, I mean, it's the complication of solving this equation we'll see in the exercise, but it's the original formulation like this, using the CI constants that are pre-calculated for efficiency on the old electrical type computer that was available in 1949, versus doing the calculation of the Ki minus 1 in the Rashford Rice equation. It's not really the efficiency part that's most important. What you'll find if you look at this Rashford Rice equation, and it's the innermost loop of the EOS flash calculation. So it's being solved many, many times iteratively. For a single flash, you might do the Rashford Rice anywhere from 3 to 300 times. The challenge is that the function itself, in extreme cases, can look like a chair, the profile of a chair, the function going kind of straight down, almost straight across, and then straight down again. And you're looking for where that chair, call it a chair-like function. Now, this is the normal way it looks. But in extreme cases, that becomes almost like a horizontal line from the left asymptote to the right asymptote. And when that happens, you get numerical challenges in actually solving the Rashford Rice for the vapor fraction correctly without material balance error. So it becomes a kind of a numerical solution problem more than anything else. But it can be a real challenge. So that's the only comment I have.
Very good, Curtis. Yeah, so I think it's time for doing an exercise now, but I guess we will do this next topic that's on fluid sampling first, because the exercise there is connected to the flash calculation. So we will do the entire exercise after finishing that topic. But we can jump to that topic, and if any of you have any questions, then please ask, and otherwise we will just move to the next topic.